Tá ótimo. Good morning, everyone. Welcome to the first international workshop on applied biosensing and also in the Women in Sensors 2024. So on behalf of the organizing committee, I would like to thank you so much for coming, and also special people that are from homes watching us. It's such a pleasure for me being here. I am Cecilia Silva. I'm an assistant professor from Mackenzie University in São Paulo. I work in the field of development of graphene-based sensors. And today we have a very special day in our event because this special day is dedicated for the promotion of a woman in sensors. So, as you know, the integration of a woman in science and technological field in STEAM is still low. Yeah, just around 30% of the researchers around the world are female in this field. And when you're thinking about the positions, the high-level positions in societies, and also the women that was receiving awards related with your research work is still a lower representative. So the focus of today is show a bit the research that the woman is doing in sensors field, and also try to pushing the promotion and integration of our young researchers, students from especially Udesc University that are here present today, to going through this career. So I would like first start giving some acknowledges from our sponsors, FAPESP, the Science Foundation State from Santa Catarina, MINIPA and IEEE, that was our sponsors also from this conference, the IEEE and the Sensors WiSE. Also, we have some very special guests today in our audience, so I'd like to say thank you so much for the presence of the rector from Udesc, Professor Dr. José Fernando Fragali, and also the director of the Research of Center of Science and Technology, that is Professor Dr. Munoz is here present today. Thank you so much for coming. And I would like to invite Dr. José Fernando Fragali for give a few words for our audience as our thank you opening ceremony. Thank you so much.
Thank you, Cecilia. I apologize, my English is poor. Then I would like to talk em português, if you allow. Bom, eu queria agradecer o convite do professor Pedro Bertemes, né, e por estar aqui presente, né. Nós somos aqui do Centro de Ciências Tecnológicas e o nosso centro, né, absorver um evento de tal magnitude, né, onde envolve tanto o conhecimento científico como a valorização da presença da mulher na ciência, né, isso para nós é um grande prazer, né, e claro o empenho completo do professor Pedro para a construção do evento, para nós sempre é enriquecedor. O professor Pedro é um batalhador não apenas pela área de bioengenharia, né, mas também pelo aprofundamento da ciência, né, e da ciência aplicada, no caso aqui, especificamente do evento, os sensores, né, que, enfim, desenvolvem, né, a melhoria na área médica, principalmente, que vai ser o tema do evento de hoje, né. Então, a minha palavra é de encorajamento, né, que vocês encontrem na UDESC o local onde possam fazer as parcerias, né, com o Pedro, com o professor Paterno, e que possam aumentar as parcerias e crescermos juntos, né, com as parcerias todas e, enfim, valorizarmos tanto a ciência no Brasil, especificamente a presença das mulheres na ciência. Então, a minha saudação e o desejo que o evento, que já está ocorrendo desde segunda-feira, tenha sucesso absoluto e seja encorajador para novos eventos a partir de agora. Muito obrigado.
So thank you so much again for the rector of UDESC. Today you are moving our open lecture for this morning. You'll be online transmission, yes? I think Professor is ready already. So you have a very great pleasure to introduce today Dr. Paola Sacomandi. She's the chair of the WiSE committee, and she's from Politecnico di Milano. Currently, Professor Paola is associate professor at the Department of Mechanical Engineering of Politecnico di Milano, and in 2021 she obtained the National Academic Qualification as a full professor. She's the chair of the Women in Sensors WiSE committee, that is a division of IEEE that is pushing the promotion of women in engineering and science, and also she's the vice chair of IEEE Women in Engineering in Italy Affinity Group. So it's such a pleasure for us have the presence, even online. We expect in the near future have the opportunity to meet Dr. Paola in person and to give her lecture as the open ceremony of the WiSE Day. Hello, Dr. Paola, could you hear me? You could not hear you yet, just a second. Could you try again, Dr. Paola?
Yes. Can you hear me well? Better?
You can, I think, increase a bit the sound. I think now is better. Could you hear us very well, yeah?
I can hear you very well, yes.
One more time, Professor Paola, sorry.
Yes, again, now?
Yeah, now is perfect. So,
okay.
First of all, thank you so much for your time and your presence and giving this open lecture in the first WiSE Day here at UDESC. We are very happy with your presence here, and even more as your representation in WiSE in IEEE is a real inspiration for us, that is women in this field. And now I will passing the stage, the online stage for you. Thank you so much again, Professor Paola.
Indeed, it's my big pleasure, and I thank you for thinking about WiSE at first and contacted me, and I would like really to congratulate for the very nice, beautiful event you have set up. So congrats, it's my honor.
So thank you again,
I will share my...
Yeah, when you want, you can start, okay?
Yes, I can share. It should be. Can you see my desktop?
Yes, it's perfect. Mm-hmm.
Okay, so thank you again. Today I'm with you with a bit of different roles. So like the chair of Women in Sensors. Also, I am distinguished lecturer for our council. So please accept that I give a brief overview regarding the Sensor Council as each distinguished lecturer is supposed to do. Well, you know very well what is Tripoli Sensor Council. It's an IEEE entity devoted to sensors in all its possible way of thinking, like theory, design, fabrication, manufacturing, application, etc., etc. Sensor Council is not a society, so to be part of the council, we need to be part of one of the societies which are associated with the Sensor Council, and we can work with it as a participant. We can be volunteer, we can sponsor event, exactly as you did during these days. The societies which are affiliated to the Sensor Council are 26, and they are all listed here. Let me just, yeah, okay. And we also have the pleasure to have more than 45 chapters, like yours, and student branch chapters. As you know, Sensor Council organizes different conferences during the year. Our flagship conference is Tripoli Sensors. This year will be in Japan, in Kobe, in October. Then we have FLAPS, we have Inertial, we have biosensors, we have APSCON, CAFE, and many others also related to industry involvement, like SIM and sensors in Spotlight. As you know, we have reference journals like Tripoli Sensor Journals, Tripoli Sensor Review, Tripoli Sensor Letters, and many other co-sponsored publications. And the Sensor Council is organized in subcommittees. There is Diversity and Inclusion Committee, which is chaired by Anna Magnani. There is Women in Sensors, which is chaired by me. Young Professionals, Industry Liaison Committee, Standards Committee, and Technical Committee, and Initial Sensors. I'm sorry, but I can hear. I can hear some voices. I don't know if it was a question for me. No, okay. In terms of distinguished lecturer program, now currently there are 14 distinguished lecturers with different backgrounds and geographical locations. And as you did with me, each chapter can reach out to the distinguished lecturer for have a lecture during their event. Indeed, IEEE Sensors Council is also on different channels like YouTube, and we have a IEEE Sensor Alert in case you want to get up-to-date information about what is going on in our council, also in terms of publications. Those are all our where you can find info regarding Sensor Council. And now let me give just a brief introduction about women in sensors. So what we do, which is our mission. The mission of Women in Sensors is to promote globally the presence and advancement of women in technical area and any profession related to sensors. And we push, we fight, we really want to highlight the excellence of females in sensor domain, because we are researchers, we do a lot of efforts, we obtain a lot of results together with our colleagues, male in our research teams, so we really want to highlight all of this. How do we highlight this? We organize several social events and technical sessions within the conferences, and also in cooperation with chapters, in order to show in which domains we are and how we alone or with our team can work. Currently, the committee is composed of 15 members from different IEEE regions, and it's interesting to see that all our members have also other roles and appointments in Sensor Council, like we have the editor-in-chief of the IEEE Sensor Journal, we have officers in chapters, steering committee and TPC of conferences, but also important roles in the IEEE, like IEEE directors, we have IEEE senior members, etc., etc. We are part of one or more societies and councils, and also the fields of application that all the members of WiSE touch are it's very broad. So we go from the aerospace, defense and security, environment, biomedical applications, MEMS, nanotechnology, photonics, wearables, and all the possible fields you can imagine. So yeah, this is WiSE, and I hope to see some from your community to join WiSE as well, even though we have a very good representation in Brazil. Okay, so thank you. Now it's start to share with you a little bit of what I do in terms of research, and feel free to ask questions and ask any curiosity you might have. So my main field of research concerns fiber optic sensors for healthcare applications. Let me start from the reason, and I believe that this is a reason which is common to all of us. So we start from a need. Which is the need? The need is to know the world we live, to know the phenomena around us, and how we can do it just measuring them. And which is the tool that allows us to measure what's happening around us are sensors. This is the reason why some of us work in sensor fabrication, some of us work in sensor application, but we try with all our energies to optimize this nice way that nature gives us to understand the reality around us. So, fiber optic sensors are just one of the huge possibilities we have for monitoring the environment around us. Fiber optic sensors usually use optical fibers in their working principle. So basically we have a modulation region, which is the part of the sensor that really senses the quantity around. We have a light source. The light is sent through an optical fiber to the modulation region, and then the modulation region, according to strain, pressure, temperature, or which is the phenomenon that it's monitoring, it modifies this light, and we have a light output, which is measured by a light detector. Sometimes the output can be on the other side of the input, or can be sent back from the same fiber in which also the source sends the light. So there are different configurations according to the kind of the sensor we have. Basically, we can classify three different sensors, fiber optic sensor types: point sensing, quasi-distributed sensing, and distributed sensing. In point sensing, actually, we can have only one sensing element in the fiber, so we can measure only in one point of the fiber. In the quasi-distributed sensing, we can measure the quantity we want on different points of the fiber, on specific intervals. And distributed sensing, basically, the whole length of the fiber can be used as distributed sensors. So theoretically, we can have infinite number of sensors along the fiber. I will give you some example of application of each type with respect to what I do in my research lab, which are in general the features of fiber optic sensors and why do we like them. So first of all, because they are electric passive, they are characterized by electromagnetic immunity, they are inert to chemicals. So in terms of healthcare application, biomedical application, they are very safe because, first of all, we do not bring any electric power in the body or in the measurement zone, in the body or on the body of the person. They are very small, very flexible, We can use them to monitor the same parameters on different points of the fibers, or with the same fiber to monitor different physical quantities. They are compatible with most medical devices and have very good time resolution. In terms of spatial resolution, it depends upon the sensor type. Usually we can have very good information along the length of the fiber, so 1D, but with special configuration we can reach also 2D and 3D information, and we should consider that there is the cross sensitivity. So if we have, for instance, temperature fiber optic sensors, it might be sensitive also to strain. This is an issue that we know, and we try to solve this with technological solutions. Being sensors, of course, they require a physical contact with the body, with the fabric, with the structure. So, but that's okay. I mean, we can leave it very well. So, what we can measure with fiber optic sensors, all the physical, chemical, and bio quantities you might think. Strain, temperature, pressure, noise and vibration, humidity, acceleration, concentration of analytes in any media. What you see highlighted in blue are the main quantities I will talk about in a while. And what do we need for measuring? So which are the main components of a setup, of a measurement setup? Of course, we need a light source, and this might be a laser or might be an LED. We need, of course, optical fiber to transmit signals, to transmit light, photodetector, a demodulator, a unit for signal processing, and data acquisition board. Let's start from one of the different technologies we might have, especially in case of single point measurement. So we have our optical fiber and we measure only one point. One great working principle is based on surface-placed plasmon resonance on fiber optic sensors. So I'm sure that you already know what it is. I'll try to explain it very concisely. So we have incident light, which is a polychromatic light that travels through the fiber core with Gaussian distribution, and inside the core of the fiber, the light will be distributed and undergo multiple internal reflections. So it will be transmitted across the fiber core at different angles. And at one specific angle, which is called refractive resonance angle, there is a special phenomenon that occurs at the interface between the metal film and the electric medium, and this phenomenon is called the surface plasmon wave. This SPW results into a sharp dip in the spectrum of the transmitted light, and it depends upon the refractive index actually of the medium surrounding the sensing part of the fiber. So basically, if we change for instance, the concentration of a certain species in the surrounding environment of the fiber, we can have a change of refractive index, and then that's why we can see this like a shift of the spectrum of the transmitted light. So for this reason, these kind of sensors are largely used to measure concentration of species in a fluid media. The main step for sensor fabrication are we have a multimode optical fiber, for instance, core diameter of 600 micrometer. We remove from a certain portion of the fiber, for instance, 1 centimeter long, the cladding. In order to prepare the sensing region, we clean this sensing region, and then we coat noble metals on the portion of the fiber. We can use gold. Gold is best, is the best metal. And then we can add another layer of nanomaterials or nanoparticles over the metal coated fiber in order to increase the sensitivity and specificity. One of our latest work was based on the use of this surface plasma resonance fiber optic sensor for detecting dopamine. What is dopamine? Dopamine is a neurotransmitter, and if we have abnormal level of dopamine, we might have several neurological disease. And dopamine is important for regulating the cognitive and cardiovascular functions, which are the typical concentration in human samples. They are around 5 nanomole, but can even be less. So we need to have very sensitive and selective sensors, and for this reason we decided to fabricate SPR fiber optic sensors, which was functionalized with gold film and some nanoparticles, which have the good, which might show a good interaction with the molecules of the dopamine, and those are the copper oxide nanoparticles. And we proved that using copper oxide nanoparticle, we could have actually a real good sensitivity for these sensors with respect to the dopamine. Whether if we used only the sensor coated only with gold, actually by changing the concentration of dopamine, the sensitivity remained to 0. Moreover, we also evaluate the cross response of the same sensor to other acids, which can live together. We can be found together with dopamine in the same fluid media, and we show that actually it's true that copper oxide nanoparticles are more sensitive to dopamine rather than ascorbic and uric acid. So that was one of our proof of concept, but of course the same concept, by changing the proper nanoparticle, changing the proper film, could be expanded to sensing a lot of quantities in fluid media. Also specific drugs or biomarkers if they are biofunctionalized. The second type of sensors, so the quasi-distributed fiber optic sensors, are usually described by this technology, which is the fiber Bragg grating technology for sensors. So basically, in the core of an optical fiber, we have a grating, and this grating acts like a filter, like a selective filter. So when a broadband light is sent into the core of the fiber, this grating, thanks to its mechanical and optical properties, reflects just a portion of the spectrum, and it's a narrow band of the spectrum which is centered around a specific wavelength, which is called Bragg wavelength. This Bragg wavelength is function of the refractive index of the core of the fiber, and F, and the grating period. So as long as the refractive index of the fiber and the grating period change because of temperature on strain, we also have a shift of lambda b in the spectrum. So if we can track the shift of this lambda b, we can definitely realize a sensor. So to better explain the sensing principle, let's consider this grating characterized by a special period and a particular refractive index of the core. We have the broadband input light. This is in green, the reflected light. If we have a mechanical deformation, so basically strain, you see that we had a shift of the reflected lambda b towards the right in this case, and if we have temperature change, the same. If the temperature change is positive, we also have a shift of the lambda b. So the sensor is highly sensitive to both quantities. I will of course skip all the physics and mathematics behind, but just to show that the change of the lambda of the wavelength reflected is a sum and function of strain and change of temperature. Of course, we need to, so we have like two inputs for the same output. So we need to be very well aware that if we want to measure strain, we need to control the temperature and vice versa. In terms of strain sensitivity, they have a sensitivity of 1.2 picometer per microstrain, and you can see that the sensitivity is constant within a huge measurement region. The temperature sensitivity is 10 picometer per Celsius degree. Those are the standard values, of course. So temperature sensitivity to temperature is 10 times the sensitivity to strain. And this is something we should take into account, especially if we want to measure a strain in biomechanics or any biomedical application. The good point of these sensors is the fact that we can realize a chain of sensors. We can fabricate a chain of sensors, which is called array of sensors. And within a few centimeters of fiber, we can have up to 40 or 100 measurement points, which is really, really a lot. With pitch, so distance, edge to edge distance in the order of few millimeters or even less than 1 millimeter. The main advantage of using this array of sensors is the possibility to monitor different quantities with a single piece of fiber or the same quantities but in many locations of the space. So if we want to measure any gradient, we can do. Sorry. The main field of application we target with these FDG sensors in my lab is monitoring temperature change in tissues undergoing thermal ablation techniques, especially laser ablation techniques. Laser ablation is a minimally invasive treatment for tumors, and it's based on increase of tissue temperature much above 50 Celsius degrees. Sometimes we reach 100 Celsius degree. So it's really important to have a good intraprocedural temperature monitoring while the clinician, the doctor, is doing thermal ablation in order to have a good treatment success, but also a safe treatment. In the lab, of course, we can we can create any complex setup we want in order to increase the dimensionality of measurement. For instance, combining more than one fibers, one or more array, we could reach up to 420 sensing point in agar-based phantoms or ex vivo organs undergoing laser ablation, and we could reconstruct just with sensors the 3D temperature map in changing in time. And this was very useful for us to understand how the temperature was distributed during the procedure. Another application we were kind of pioneering was the usage of fiber optic sensors to monitor thermal ablation of breast tumor in mice undergoing photothermal therapy. Actually, in that case, we didn't have just laser, but we also had gold nanorods inserted inside the tumor in order to enhance the absorbance of the near-infrared light of the laser inside the tumor and having a more specific and targeted and selective treatment. And we could study the thermal effect of different laser parameters, so basically the wavelength and combination with different gold nanorods size in order to see which was the most effective combination to achieve the required temperature change inside the tumor of the mice and at the end to kill the tumor. Of course, in this application of photothermal therapy, where we use nanoparticles, we need also to know before the insertion of nanoparticles in the tumor, which is their thermal response. So thanks to Faber-Bragg rating sensors, we can also we devised a very nice setup to characterize the thermal response of a huge quantity of nanoparticles, copper oxide nanoparticles, gold nanoparticles, polymeric nanoparticles in hydrogel. And the use of nanoparticles and the combination of temperature and nanoparticles is useful not just for photothermal therapy, but also for temperature control release of drugs. This is a study undergoing in collaboration with chemical colleagues. Another possibility, since inserting a few fibers inside the organs is quite feasible, and we can have temperature information on really a huge number of points, we also use this technology a lot for validating numerical models we developed to predict the thermal response of tissues, but also for estimating unknown tissue properties, thermal tissue properties, which can affect the result of the thermal therapies. Do you remember I was mentioning this cross sensitivity between temperature and strain before? If we work ex vivo, of course, no problem, nothing moves. But if we want to measure temperature during a thermal treatment in person or in an animal, we have the strain basically due to breathing motion. And this can cause a temperature error which can correspond to 2 to 5, but even higher, to 10 Celsius degrees. So we need to be very well aware of this problem, considering where we are measuring the temperature. So knowing that the tissue deformation also depends upon the anatomical location of the treatment zone, and we can also implement, and this is what we do, a real-time signal processing stage in which we filter out the component of the strain of the breathing, and we can have a good measurement of temperature without the effect of the strain. Very briefly, I'm mentioning a slightly different technology, which is still related to Faber-Bragg rating, but this time they are called tilted Faber-Bragg rating sensors. So what happens here? The grating is tilt. The grating is in the core is tilt, and this tilting causes a coupling between the core and cladding modes. So basically, we have some cladding modes of the light which can interact with the surrounding environment on the outside of the sensor, and this allows to have other measurements, like for instance the surrounding refractive index. So the idea was to use this technology to monitor not just temperature but also refractive index, which is also a function of temperature, refractive index of biological tissue undergoing the thermal treatment. And we developed my team actually developed a very nice model which allowed to reconstruct with the signal obtained with this tilted FVG the temperature distribution across the sensor, but also having information about the refractive index change due to the thermal damage of the biological tissue. What happens if we do a thermal treatment? Actually, we have the laser shine in the tumor, so we have an accumulation of energy and temperature in the tumor, which causes certain thermal damage. Sometimes it can be challenging to have a control on the shape of this thermal damage. So we devise an approach. We devise an approach based on the control of the power of the laser based on the temperature measured in the tissue with the FVG. And this allows us to have a good confinement of the thermal damage according to the dimensions that we want. And we applied this concept to the laser ablation control of different organs like liver and pancreas. Still talking about FBGs, because it's a very nice technology, let's not forget about temperature and let's think about strain. So we are developing 3D printed smart patches. So it's very simple to 3D print any shape and structure that you want and embed during the printing the fiber Bragg rating sensor inside. Actually, this allows also to have a good intra-procedural monitoring of the embedding process. Of course, there are many parameters which can affect the performances of these smart patches, like the materials which coat the fiber optics, which are acrylate or polyimide, and also the material of the patch, so the plastic, basically the polymer that we use. So before to do anything, we made a very deep characterization of the combined effect of different coating of fibers and polymer of the 3D printed materials. And then, after this characterization, we decided to use some specific cases, so some coating, some material, to start developing wearable devices. And the first application we did was towards classic ballet dancing. So actually, during classic ballet dancing, the dancer is subject to very, say, strong physical activity, which can bring to also pain and serious problems to his body. So it's important to have a proper monitoring system on the body of the dancer, and there is not a lot right now. So the first step we did was to define a wearable device for measuring the anklet movements during the execution of a specific exercise, which is called Batte Mountain Dew. This is a picture of the anklet, which was 3D printed with TPU material, which is very flexible, and we embedded inside an FBG with an FBG array with 5 FBGs. We characterize this structure in terms of curvature in order to have really a monitoring system of the curvature of the foot of the dancer, and we compare. We ask different dancers, like a professional one, amateur dancer, to wear the device and do a specific exercise. And it was very interesting to see the results. Of course, to have a good interpretation of these results, we would need a dancer. I'm not a dancer, I'm not a professional one, but we can clearly see that, at least in terms of standard deviation, dispersion of data for the single sensors and during the same exercise, the professional dancer is it's better than the amateur one. Then the really last application regarding FPGs that we do in our lab is to define a monitoring system for prosthetic foot, 3D printed prosthetic foot. Why 3D printed prosthetic foot? Because of course we have reduced cost and also bigger flexibility in terms of design parameters. So one big part of the project was related to the definition of the best concept of the prosthetic foot, and in all those concepts we embedded the fiber Bragg rating sensors in specific locations in order to monitor the mechanical behavior of the prosthetic foot before to be worn by the patient. So we did quasi-static tests, like simulating I don't have the name now, the way a normal person should walk, like heel strike, mid stance, and two off, by changing the angles of the prosthetic inside the testing machine. We also performed cyclic tests in order to study the robustness of the prosthetic foot in time. Yeah, this is the video. And what we could observe is that, of course, this being a kind of, let's say, energy storage and release prosthetic foot, there are different behaviors when the prosthetic foot is loaded and is unloaded, but the most important interesting result is this one, is that for the material that we choose, we could see a gradual plastic deformation of the material, and also we could observe the difference in terms of strain measured by the FBGs when the heel area of the foot was damaged. So, regardless the performances of the prosthetic foot, which are for now not the best, we are still working on this. At least we could conclude that our monitoring system based on FBGs was very effective to see all these phenomena that we could not observe in other way. The very last part of my talk is related to distributed fiber optic sensors, which is the third category. Actually, there, all the length of the fiber can be used as a sensor, so we do not need to have a physical sensor fabricated inside the core of the fiber. So this is different than the SPR sensor and the FDG sensor. Basically here we use the backscattering of the light, which is function of strain and temperature. What is the cause of this backscattering? Considering the main phenomenon, which is the electric scattering, we have the elastic distribution of the light inside the core of the fiber occurs in all the directions, and this is due to the interference of the light with the small particles, which are part of the material of the light itself. So, the backscattered portion of the light caused by these small particles is called the backscattered light, and this backscattered light is function of temperature and strain, and it represents a sort of fingerprint of each optical fiber. We can process the signal, the backscattering signal, in terms of in the time domain, so obtaining what is called optical time domain reflectometer, or in the frequency domain, which requires to study the interference fringes of the backscattered light from a tunable laser source. I think it's not the time to go too much into detail on this, but let's consider that basically we can kind of realize some virtual sensors along the length of a distributed fiber optic sensor. If we have temperature change or strain this results into a shift of the spectrum of the main frequency of the light, which is backscattered. And similarly to what is done for the FBG, we can consider to have a sensing element length and a specific spatial resolution. The only time we used this technology was to evaluate which was the best between distributed sensing and FPG, because both are very valuable, but actually we couldn't find any work which could benchmark one against the other one. So we defined a setup which simultaneously we put different FBG arrays, so with different grating numbers and grating lengths, and a distributed fiber with theoretically say the all active fiber length, and we could study the signal to noise ratio and also the distribution, the dispersion of data. And what we obtain as a main result is that regarding distributed fiber, an improvement of spatial resolution meant an increase of the noise. So a lower signal to noise ratio. So there was always this trade-off between spatial resolution and signal. That's why at the end it resulted that FBG sensors were the best option in terms of both signal to noise ratio and standardization. So yeah, this is like the final summary of the long journey. I try to to summarize as much as I could. Those are again most of the applications that we do in our lab, and I'm happy that I could share them with you. We are a very nice lab with more than 10 staff members. We are in Milano, in Italy. Always looking for PhD students. So in case there is someone who is interested, please drop me an email and we can have a discussion. And I would like to thank you again for your time, for your patience, and open to any question.
Let's thank Professor Paola. Thank you so much for a fantastic talk and a very innovative work, Professor Paola. It was great to have you here. And now you are open for questions in our audience. So I will start with one question. I think it's really interesting the use of the fiber optics for mechanical sensing. I confess that was the first time I saw this application. I would like if you can do a comparison between the difference or the benefits exploring light for this mechanical sensing, as in the prosthetic foot, when you compare with the traditional capacitive sensors or piezoelectric sensors.
Yeah, actually the main reason why we choose to use FPGs for prosthetic monitoring was because with the single fiber we could monitor the prosthesis in at least 4 points, but we are working towards much more points. So I don't know if it is visible from from this is the video. You see, we have only one small cable, and so the monitoring system is it's really light, and there is no big there is no discomfort at all for the person who should wear the prosthesis, and we could have with the same single cable up to 40 measurement points. So that's definitely a big advantage over any other technology.
Okay, this is really interesting. Thank you so much. And other questions from audience? Yes.
Congratulations for your presentation. I'm Alexander Paterno from the group of optoelectronics here at UDESC. So I work with relatively similar instruments and topics that you are working, and some questions I would like you to clarify for the audience also. You probably didn't mention, but I suppose that you are using mainly silica fibers. Can you comment on the use of different materials for example, more frequent use or daily use of sensors in biomechanics and also other applications that could be more sensitive or even more resistant to mechanical efforts?
You mean more robust than the silica fibers?
Yes, in this case.
Yes.
But I understand that it can be also robust using silica fibers. But you can comment because you have shown a lot of experiments, so you may have more to clarify for us.
Yes,
Right.
thank you for the question. It's really important indeed. Yes, it's true that silica fibers can be fragile. That's true. We need to be very delicate and careful when we handle those fibers. However, with the good packaging, and this is what we work on every day. So protecting the fiber, embedding the fiber in a case which is optimized to the specific application. That's the sensor becomes very robust as any other sensor, more traditional sensor, I would say. Still keeping the advantage of flexibility and low weight. So for this. Yeah, you need to be careful. You need to know which are the limits. Yeah, it's true that one of the biggest limitation is the curvature radius, which is in the order of 5 millimeters at least. So you cannot bend the fiber too much. But still, 5 millimeters, 1 centimeter for all the mechanical applications we work on is completely doable. So yes, that's the main comment I would say. Then there are other materials the fibers can be fabricated with, like plastic fibers. I've never used them, so I cannot say too much. But there are other possibilities as well for light guides.
So, thank you. It's fine, Professor?
I don't know if I replied to the questions or if...
Yes, that's clarified because it's important for our students also to know the experience outside the university here. Also, it's very important international experience. Another question which you didn't mention, but probably there is a lot behind that, is about the interrogation of fiber Bragg rating sensors or even the OTDR that you mentioned. How are you doing? Are you doing for using the most recent equipment that are usually very easy to manipulate and you can take it with you as a portable device? Or are you using benchtop equipment which would could be much more efficient depending on the system? Or you are implementing your own interrogation systems in your labs, right?
Thank you. Another important question. I didn't mention, we, for FBGs, so for the interrogators of FBGs, we have both solutions, all commercial solutions. Actually, we do not have the capability to develop our own interrogators. But we have like the Hyperion, like the classic old, it was called the Micronoptics SE255, which is the state of the art, the best device for FPG interrogations in terms of measurement range, so the broadband range. But we also work with small, let me show you, interrogators, which are 100 grams in weight, for developing wearable systems. So this is completely portable. The one that you see now in the picture is not portable because it was connected to the laptop, but we developed also our wireless version. So we have the portable version. There you can connect only one fiber, whether with the standard interrogators you have more than one channels, usually 4, 8, we have 16. But then it's okay. I mean, as long as we can just have more sensors on the same fiber, as I was mentioning before, one channel is enough for us. Regarding the distributed sensing, we use the bulky equipment ODCB, which is not portable at all. Yeah, that's one of the limitations of the distributed sensing technology.
So thank you so much. You have one more question, Professor Edwin.
Thank you so much, Paola, for this fantastic talk. This is Eden Morales from National University of Mexico. I'm very happy to meet you. I'm curious about the engineering behind your wearable device. So you already mentioned that it's a portable reader, maybe. So I'm curious about the wiring, and I'm curious about the vibrations. If you have any noise because of vibrations and this kind of details.
You mean, for instance, on this application on the prosthesis or in general?
For the dancers.
For the dancers. Vibration, what do you mean? Here, the main, not for the anklet actually, we are developing also other wearable systems. The main confounding factor is the temperature in these specific applications. In terms of vibration, honestly, we didn't think about it, but we didn't really have the feeling that it was a problem. Not on the, nor on the portable interrogator, neither on the anklet or on the other wearable devices we developed. So there the main issue is the body temperature, which is the sensors, and we have to compensate for it.
So is it really comfortable to wear, or maybe the dancers have some feedback about the wearability?
The dancer so the movements were not disturbed by the presence of this anklet. Both the girls, the dancers, different dancers, so they could do their exercise like they were not wearing anything. So that was completely okay for them. That was their feeling. I'm not the dancer, so I didn't wear this anklet. I cannot say.
Thank you so much.
Thank you so much.
One more question from audience. I think I just have the final question again, Paula. Fantastic work regarding this thermotherapy for the cancer treatment. And are you also exploring combination of some molecules that could generate an oxygen reactive species, ROS, for this treatment, or just focus more increase of the temperature?
You're mentioning about this application, right?
Yes, is this golden rods? Yeah.
Yes, we measure only temperature. We are specialized only on this, but there is research ongoing in other labs, also monitoring of, let's say, immuno-related bio quantities, biomarkers. So yeah,
so
you're absolutely right.
That in future could combine like diagnostics, therapy, and diagnosis and therapy simultaneously. Yeah.
Yeah. Yes.
So thank you so much again, Professor Paula. Let's thank again Professor Paula.
Thank you. Thank you again.
It was a wonderful lecture. And now you have a short break, I think half an hour, and you're back 10:30 for a presentation, another lecture. Okay, thank you so much again.
Thank you.
Bye-bye, Professor Paola.
Bye-bye.
It was a pleasure. Meet you online, at least.
Yeah, I'm sorry I could not be with you. It's a critical time for classes.
No, I can
Yeah,
imagine you are in the end of the semester. We
yeah,
really hope
yeah.
we host you here in Brazil in another opportunity.
I look forward to it.
Coming to summertime. Bye bye, Professor.
Yes. Bye bye. Thank you. Bye.
So you can start, yeah? Okay. So thank you so much, everyone, for coming back for our special section today. Now I would like to introduce the lecture of Dr. Gabriela Soares. Dr. Gabriela is the co-founder and administrative manager of Health Tech NanoCantech Solutions. That is, I think it's not more, it's startup company, yeah? And because they are so big right now. And she also works as responsible for research development and innovation chemistry area with experience in promoting research agents such as investments in research and development. So today, Gabriel will talk for us about the use of biosensors for monitoring pathogenic microorganisms and prevention infection in hospital environments. So thank you so much, Gabriela, for joining us. It is our pleasure receiving you.
Thank you, Dr. Cecilia. Thank you for the organization's committed to the environment. And I started to say sorry about the hospital. It's missing an A. So let's start. My name is Gabriela. I'm a chemistry. And now I'm talking a little bit with you about what is the NanoCantech solution and what NanoCantech solutions work in biosensors field and helping prevention infections. NanoCantech Solutions was created in 1918, and we started in a PPFAPESP. It's an agency that's financing our projects. In that moment, me and my partner was only academic researcher. And we starting to learn more about something for startup running and startup creations. Now we have 3 pipe FAPESP projects finished and 1 Cibratec Nano project, FINEP, is still in progress. This Cibratec Nano, it's started a new area for the development for NanoCantech solutions, that is the agro areas. We won a Startup Day Awards, lead Startup Day, and nowadays we had 500,000 invested and RD&I. This is our team. It's a diverse team, motivated one. I am a CEO and co-founder. My partner, Margaret, is CTO and also the co-founder. She is professor of medicine faculty of the São José do Rio Preto, FAMERP. We have financial and strategic advisors and TE support, and also a lot of girls who worked in the PD. We have also partners, such like Filippo Gigliano from UFSCar, Dr. Cauê Ribeiro from Embrapa, FAPESP, Parque Tecnológico de São José do Rio Preto, and a company, Visual Systems, that work with us with the project HIT. So, I'm a scientific researcher by love and profession and a manager by functions and passionate about innovations. I did my bachelor degrees in UNESP, working with environmental chemistry. Then my master and PhD, I worked with sensors, especially sensors development by using in agrochemicals. And I started working with sensors in my master's degrees, developing sensors to identifications of pesticides in soils using electroanalytical methods. In my PhD, I worked with some synthesis of nanomaterials and also photoelectrocatalysis. And when I finished my PhD, I have a lot of opportunities. And one of these opportunities is to create a new company or a startup based on research, and then started NanoKentucky. NanoKentucky works basically in monitoring of pathogenic microorganisms and hospital infection prevention. And to start to talk about this field, I would like that you think in someone that you appreciated, that you really love. Someday, this person have to go to the hospital and then needs an emergency surgery. In that surgery, it's occur everything fine, but one day, or she is stayed in the hospital to be observed, the health stations, these stations begins to worse. And the doctor said that this person have healthcare associated infection or hospital infections. And we think about it. What you did wrong about all these treatments? Should I get some dispositives or some medicines that avoid to not occur these infections? Out of 100 patients in acute care hospital, 7 patients in high-income countries and 50 patients in low and middle-income countries will occur at least one healthcare-associated infection or hospital infections during their hospital stay. On average, one in every 10 affected patients will die for infections. This damage is not, it's a big damage for the family, for the patients, but also it's a main pain of hospitals. Why? Because in hospitals situations, it's increase also directed and indirected costs. Treatment for patients with infection is a double than for the patients without infections. We know that for the infection control, we have to work with different pillars that you say, and some of these pillars is environmental hygiene conditions. This is kind of a pillar that you experiment in the COVID pandemic. Hand hygiene protocols, and also medication prescriptions. And NanoContact Solutions work with 2 of these pillars: monitoring of environmental hygiene conditions with Infect Detect kit, and training and awareness of importance of hand washings using protocols. If you take a look very closely in the hospital environmental, we could see some critical points. These critical points, it's conducive to microbiological proliferation superficies or surfaces. For better control of infections rates, these critical points should be identified and monitored constantly. Infect Detect so work with identifications of pathogens on inanimated surface. And how it's work? We have some biosensors, disposable kit made up of nanotechnology and specific bioreceptors for each microorganisms. These kits communicated with IoT, with hardware developed exclusively for this purpose, for reading these kits. And we have also an applicative and a software with algorithms for processing and treatments of these results, and how it works in hospital. Actually, at the first we find critical points on surface around patients, thinking about where it's the most probable surface that should be contaminated. Then we choose the specific biosensors. Now we will still have in development of others biosensors, but you already have Staphylococcus aureus, Klebsiella pneumoniae, Escherichia coli, and Candida albicans. Then we selected the samples by flocking swabs and insertions in a specific reagent. This reagent is inserted in these kits to finally reading by hardware using AI. This is the what looks like the application, and to see that is very small and it's not so complicated to manage. It takes some videos. The results here, we can obtain it until 30 minutes, and it's very fast compared for the culture of microbiological culture to get the results. Now we already have some development and validation in hospital environmental. Focus on the qualitative methods. The last one that we validated was in HCM institution, that is the Hospital for Child and Borns, UTI neonatal. These projects we just validated and collected in 5 points: the locks or support for opening SafeIt, patients handling, so it's the 2 of points, the input of supplies, and the removal of disposable diaper. About this validation, we could obtain some very important results. For example, sensitivity and specificity for Staphylococcus aureus. Also, the precision, it's more than 90%. For Klebsiella pneumoniae, we already have some good results. And this Salmonella, it's for our another project related to the agro field. And this, we didn't validate it in that scenario, in that hospital scenario, but we validated in another scenarios, and we could get a lot of good results also with this kind of methods. And now, what is the state? What you're doing? We are in a second validation. This validation, it's a long time validation, already until 2 years. And we are connecting to commercial and productive partnerships to create the partnerships and to actually found some commercials better issues. Now we have some kits that it's low cost. However, if you increase the productivity, we already know that this cost could be lower. The second point about control infection is the hand hygiene. The hand hygiene significantly reduces the transmissions of microorganisms and reduces the incidence of preventable infections, increase the safety of patients, healthcare professionals, and the general population. And the strategy for nanocleantech solutions to help this pillar of control, infection control, is using what is called protocols. Protocols, it's composed by 3 devices. A device that is installed in the budget, so from the collaborations, or the hospital collaborations, we installed some just devices in the budget. Then we have another devices installed on the wash point device, the wash point, and the another one in the bed point. All of these devices is communicated, and then we have some results. If it's the protocol, it's okay. It's defined and produced and executed fine, or not. So we have the red part that is related to that should be better the results or control the results. And this in green one, it's that the protocols, it's okay, it's fine. So, first of all, we have the protocol settings embedded registrations. Then we installed the devices over the sink. The devices over the sink, it's very, couldn't see here. But this device is identified what is the person is that in front of this device. So as we already have the registrations, we know also the name or a code that you give for these collaborators. Then the next step is wash your hands and go to the bed. But if the person that wasn't washing the hands and stayed in front of the bed, another device that is similar with one in the sink device, identified also that person. So that person identified on the bed, it's also say, okay, you washed your hand and go on. You can take care of the patient. So it's identified the person, and we have a green light. Or if the person did not wash her hands or his hands and stayed at close as the patients, this device also identified and say, no, you didn't wash in your hands, so you should come back and wash your hands. All this, as I said, it's presented for each person or for each collaboration, or in the case could be presented also for the director of the hospital or directors of the control infections specificities or in the hospital, to see if the protocols will be made fine, or if the protocols should be implemented or should be give some more investigations or some more practice or some more training for the collaborators to do these protocols. And the state of this kind of technology, nowadays we are just looking for angels customers. On the other words, we are looking for some hospitals that just give us the place and some supplies to apply this technology and make this some tests or some extensively tests to see if it's really work during a long time. And finally, the kit, the Infect Detector kit, already have some issues that we see it's a good to collaborate it. One of these issues is, okay, we identified microorganisms. We could identify microorganisms in health field or in agro area or in such of areas that it's a problem that these microorganisms stay there. In this case, what we could insert in this prediction, or we could have a predictions using kit infect detector and IE, artificial intelligence. And thinking about this, we created a partner with a visual company, Visual Systems, a company that we have such microbiological tests and send these results to these companies, to HITS. And what HITS does? Visual Systems, or HIT, have some sensors that control infection. Infection control is, of course, NanoKintech who gives the results or who sends the results. But electrical systems, predictable of outbreaks, patient comfort, water supply, cold chain, air quality, and HVAC, all these kinds of field, visual systems have some sensors that could help to see if this field is working along the environmental or along the hospital life. What do you mean? For example, supply water. They have some sensors that is installed in the supply water to see if have some problems about this supplying water. Or another one, it's code 10. They have another sensors installed in all of these code 10s or devices, collecting, for example, internal temperature or some humidity, some electrical signs, to see if all of this worked fine or is working fine along of the hospital life or hospital processing. And all of these environmentals generated some data that is could see in different manners. Here is another one, the air quality, which is sensors for visual systems worked, and it's just to give the idea for the hospital that is the environmental, it's fine to work or not. All of this is generated in real time. Okay, so it's fine for it's a good thing for the environmental, for the hospital to monitor in real time. And of course, we are just sending some pathogens when you are making these results or these analyses for the visual systems. And all of this data is pathogens, carbon dioxide, particles in air, temperature, moistures, luminosity, atmospheric pressures, noises, and another of data. We just trying to create an artificial intelligence to predict along of the years what kind of different or what kind of change in physical parameters could indicate and stay or created or identifications of the microorganisms in that environment. But as I said, we send the results for our measurements for the visual systems. However, we already have these results in our hand until 30 minutes. And we would like to say that when you work in hospital environment or any hospital that we are working, we doesn't want to take a look and see like this. It's a positive, for example, a Salmonella or a Staphylococcus aureus or Klebsiella. We would like to see like this. It's a negative. So I appreciated too much your time, and I will open, of course, for some questions if you have. And the NanoKintech also using science to produce new technologies with the objective of improving the quality of life. Thank you very much.
Thank you so much, Gabriela. It was fantastic talk, and first of all, congratulations, because we know how hard is this path for become entrepreneur in science technology, and you really need the people with a strong and brave for you really have our technology going to the market. So first of all, let's say congratulations for you and your team for accept this challenge and showing wonderful work today. So you are open for questions for Gabriela. Yeah.
Hello. I wanted to congratulate you also. I know how hard this can be. I had a startup company that failed, unlike yours, which seems to be a success. And I'm really happy to see people trying and doing it. It's really hard, but I think it's incredibly important for our country and for healthcare as well. I was curious, how does the first equipment you showed that detects bacteria, how does it work? How do you detect bacteria, and how can you be sure that it's detecting E. coli or Salmonella or Candida instead of detecting other microorganisms?
Yes.
And how much do these cost, the replaceable things? So how much would a hospital have to spend to keep testing this over and over?
Okay, thank you for a lot of questions, and thank you for the congratulations. Nowadays, I still stop sometimes and thinking about it. Oh my God. Okay, this is it. Come, let's continue, because it's a lot of hard time. So let's see about what it's or how can infect detector work it. Actually, this is a radio frequency sensors. Okay, so we already have some disposal. This is constructed as a biosensors. And these biosensors is we using a specific bioreceptor for each microorganisms. This kind of microorganisms will give some results using our hardware and intercommunications of these two equipments, okay, biosensors and our hardware, and give some datas. These datas we started to correlate it with some changes using these bacteria or not, using the Staphylococcus aureus or the Salmonella aureus. The Salmonella spp, okay? And how we can prove that? How can you prove that this result is do it only for this kind of microorganisms? We already have a lot of knowledge about microbiology. So we worked with some plaques or some mediums that only development this kind of bacteria. We use only the ATCC SIPs, okay? We doesn't use another kind of bacteria. So in our lab, we have some kind of routines that we create the sensors, or we created or adapted or smooth some parts of the sensors, and then we have to the standard methods, that is the culture, microbiology culture, and we check if the microbiology culture it's okay, it's increased that kind of microorganisms, and we have some changes in, for example, we use the reagents with the microorganisms, or we use the reagents without these microorganisms. We take a look at the results, and you see that have some differences, okay? I was talking with Cecilia that in the first time it was very hard, because we doesn't know very well what kind of these changes could occur, what kind of distant we could take a look to see that this is biosensors, okay? Because we have a lot of changes, a lot of variables, and these kinds of things we started to work at with algorithms and such kind of processing treatment, okay? I would answer you. I forgot. How much? Yeah, I forgot one. For the laboratory produced, nowadays we have around, for these sensors, we produced about 190 no, 200 reais. Okay, it's not so much. But we know that when you are producing in the commercial thing or some like a big productions, we know that this cost will decrease. Okay.
Just a complementary question related to this, but this is the cost of the portable reader,
No,
or
it's
is
the cost
stripe?
of the biosensors.
The biosensor.
The cost
okay.
of the portable reader is about 500.
Okay.
Okay.
Thank you so much, Gabriela. You have one more question?
The very inspiring ideas.
Thank
Because I would like to ask you, where are you using it? You're not, for example, that equipment that shows the detection of hand hygiene, for example.
Yes.
It rings an alarm when it detects that the person that nears the bed in the room did not follow the protocol. What happens when it operates?
Yeah.
When and it's based on the RFID badge.
Yeah. This one, the protocols. Its equipment doesn't identify microorganisms. Okay.
Yes.
Just identified the presence, the person presence in front of him. Okay. And then how it's worked. When the collaborated just wash your hands, it's registered here that that kind of person is stay there washing your hands and during such time. Okay, this is an important thing because if you just pass by this equipment, it's not related that you wash your hands. Okay. And then when that person is stay in front of the bed or besides of the bed, if it's not registered that this person doesn't wash his hands or her hands, it's also registered. And here I just forgot to say, we have a light, a red light, and you also have a sign, okay? So it's dispensed and beep, okay? And say, okay, you have to come back and wash your hands. This beep should be optional because of this kind of environmental that you are using. Yeah, we are working in a hospital. And in this kind of thing, or in this kind of issues, is related in the red. Okay, and then you ask me, okay, but you identify that he doesn't wash his or her hand, and what do? It's not my choice. It's not my manage. I just give the information for the responsible of the hospital, that is the infection control responsible, to say, okay, you have to be training your team, you have to change your protocol. So it's such information that give for these responsibles to change something that it's related to the control infection.
And this badge is based on a common badge, ordinary badge with the RFID, is it?
Yes, yes.
Oh, I would like to know the cost of that, the whole system, for example, to apply in kids, so that we can teach them to wash their hands, for example, or in a school. And the alarm would ring not as an alarm, but as some screen with a clown saying that it.
This
Because
big
that would
screen,
be exactly the same solution.
could be applied also.
Yeah.
However, this kind of equipment, we are in development. We are changing some parts and we are increasing in other parts. Okay, in this kind of things, I don't have, for example, until time some confirming we're using 2 sensors in this kind of environmental hospital. Okay, so now we are in development, and I think until the end of this month we already have the next version, or the improved version. We know how much it costs. Okay, now I can't say that you're okay, it's costs just this.
More questions to Gabriela?
Thank you so much, Gabriela, and congratulations
Thank
for
you.
your results. I was wondering about you showed something related to the specificity and selectivity of your test.
Yeah.
And I was wondering about the gold standard that you use to establish these measurements.
Okay. We use the culture microbiology standard. Okay. We know that when you go to the environmental validation, we have some variables that we doesn't identify it. This kind of sensitivity and specificity is in lab. Okay. So we have a control environmental. We made, for example, the specificity, and then we made just interferences, okay? Just interferences tests to another microorganisms to see if this kind of a bioreceptor or constructors of biosensors have a specificity or a selectivity. Okay, fine, okay. For the next step, that you go to the environmental validation, as we don't have all of the variations or variations listed or know it, we know that this kind of precision and specificity will decrease. Okay? As we are finishing this kind of validation, we doesn't have anymore, or we doesn't have yet, okay, this precision or this type to give you.
Thank you.
But as we are working, or as you're finished, I can send you, no problem.
Thank you.
Welcome.
So I just have also a complementary question regarding the Eden's question. How is the sensitivity in terms of CFU, the units of bacteria you can detect? I don't know if you can say these numbers, but how is
the low detections?
Yes,
Okay.
in this case.
We worked in a range from 20 and 1.10 elevated to 2, and 1.8 elevated in 2. Okay, it's kind of range to see what kind of limited we have. Okay, we validated this until it's worked in all of this range, but in each microorganisms we have the limit detected. The limit detected, specific detections. But it's range about 1 point elevated to 100.
That is the clinical relevance for the
yes, for the environment. It's okay.
Perfect.
Okay.
So thank you so much, Gabriela, and thanks again for the fantastic work.
Thank you.
So now you are moving for the student section presentation. I don't know if is Afonso already here? Yes. So now you have a oral presentation of Afonso Henrique Batista, and I think he's a student from the research group of Professor Alexander Paterno, yeah, from UDESC. So, Afonso, he'll present his work regarding is the embedding of impedance electrodes on a surface plasma resonance fiber optic sensor feasible? Oh, it's a question for us. Very good. So you can start. Thank you so much. Do you prefer this microphone?
Good morning. My name is Afonso. Thank you. Good morning. My name is Afonso. I'm a student here from UDESC, undergraduate student, and I am doing a scientific initiation with the group of fiber optic laboratory with Alexander Sade Paterno. And this semester we start to studying optical fiber sensors. And then we wrote an article that is more an idea, so it's not a concrete conclusion. And this is the embedded impedance of electrode surface plasma resonance fiber optic sensor feasible. And here we will discuss, sorry? We will discuss about the behavior of the surface plasma resonance under a lot of situations. Some situations about the size of them, the number of electrodes, the polarization, the applied current, and methods for enhancing the sensor. As I said, there is not a concrete conclusion, and this is more an idea for a discussion. But first of all, what is a surface plasma resonance? A surface plasma resonance is a phenomenon that occurs when a thin film of gold is placed under a glass plasma and is shooted a polarized light. As we have there is a laser. This laser should be shooted in a very specific angle to reflect in the glass under the gold, thin gold, and this light goes to a detector. Okay, the interaction of the light with the gold will generate oscillation, excitation of the free electrons on the metallic plate, in this case is gold, but can be silver or other metallic materials. And this oscillation will generate a evanescence wave that in a specific frequency that is the same as the frequency of the light. It will generate the surface plasma resonance, and this will make a how can I say? This is okay. The surface plasma resonance will absorb the light of the laser, as the next slide will show here. An example of experiment made by Dave Coulter, that he shot a helium neon laser into a prism, that behind this prism was a 55 nanometers gold film. And this prism reflects the light through a wall, and a specific one that was about 46 degrees appeared the surface plasma resonance effect phenomenon. As you can see there, the laser, I don't know if you can see because of the light, but the laser is not continuous. There is a lack of color right in the middle of the laser. This is the effect of surface plasma resonance. We can see here in this graphic too that if you can see there, the green line one is the espessure of the gold, about 50 millimeters, and we can see under there the angle about 44 degrees. There is a like a hole, that meaning that is the lack of light, lack of reflection of the light. That is exactly what's happening in this image there. Okay, now going to start the some behaviors in different situations. The first situation is the bioimpedance sensing platform with designed electrodes. What happens if we measure this with 2 electrodes in a bipolar measurement or in 4 electrodes in a tetrapolar measurement technique? In 2 electrodes, there is a much easier technique that uses just 2 electrodes. So the advantage is his simplicity. Another advantage is a low cost, but in the other hand, is a much low. It has a much low accuracy in this measurement because the current and the voltage there is measuring the same electrode. On the other hand, a tetrapolar measurement technique uses 4 electrodes, but is a much more complexity way to measure, and expensive, and more expensive. But this method, we can measure the current and the voltage at the different electrodes, so it's much more accurate, much more precision measurement, although it's more expensive. In this case, the surface plasma resonance are very usual to use the evaporate films as electrodes, and it's usually used as 4 electrodes, and the technique of 4 electrodes to measure because of his much more accuracy, and for the use of this is more for biological uses is much more it's much better. Another situation is what happens if we reduce the electrodes 10,000 times or about 10,000 or 100,000 times. It obviously will make the sensor much more accurate, much more precise, and that he can now with this little size measure biomarkers as DNA, antibodies, proteins with much more precision. But if we reducing a lot of, like 10 times, 100 times, 1,000 times, it will cause a lot of susceptible variations. As the temperature variations, this will be very sensitive. In chemical composition of the media, so too, it be very sensitive. And obviously the price. Even lower, if you shrink a lot of the electrodes, it will have a very high price because the size is inversely proportional to the price. Then that depends of the experiment you want to do. You need to be if it is worth to shrink a lot. The influence of the current in the electrodes on plasmons. If you insert a current in the electrodes, it will cause a lot of heat. This heat can change the intensity of the plasmon propagation and modify the electrode density of the metallic surface, causing the altering the frequency of the resonance of the plasmon. And that means that if you apply too much current, the angle will change, or depending of the angles, depends how much is the current applying the in the electrodes. This is a lot of used to calibrate the plasmon to different analytes that can be an oil that you put between the glass prism and the thin gold, and for different materials of the metal, too, silver, gold, you should tune this with the applied current. But there is a problem if you apply the current. That is the thermo-optical effect. The thermo-optical effect is the effect that occurs when you put current in the electrode, it changed the temperature, and the temperature changed the index of reflectivity. It can change the permissivity constant of the metal, and it can shift the wavelength. It can cause a lot of problems. So to avoid these problems, you should to take a more accurate results. You should choose a material that has a higher thermal conductivity to minimize the effects of heating. Okay, the effects of the polarization and the polarization of the electrode and the relevance of this is that the polarization can change the sensibility, the stability, and the accuracy of the experiment, of the measurement. The sensibility, you can use the polarization to optimizing the angle that you throw the laser to the glass in a more precise way. And the sensibility you can detect some changes. The change of polarization, the control of polarization, is used to detect some change, like detect molecules, the interaction of molecules, and proteins, antibodies, and more. And the polarization is used to control the stability of the sensor, avoiding the noise, making a reduction in the noise, reduction in the stabilizing the temperature of the sensor, and more. And the polarization is used to make the sensor more accurate, make a reduction of the systematic errors, and determination the resonance peak, determining the resonance peak, and more. However, is very interesting to a sensor. You have a control of potential differential between the electrodes, just to avoid the variation of signals as the temperature changes, to make it more stable. Here is a comparative analysis between optical and electrical spectrum. Each one has your advantages. Like the optical spectrum is one that transmits data in a very high speed. It is immune to electromagnetic interference and is used to applications that require high precision and a quick response times. And the electrical spectrum is a spectrum that uses the electro characteristics to make the measurements as the current, voltage, resistance, but it's very susceptible to the electromagnetic field, is more sensitive. But one way to take the better of the two spectrum is to make a hybrid sensor that use the spectral of spectral optical and electrical to put them together. The optical sensor can be used to monitor rapid subtle changes in the environment, while the electro sensor can provide complementary information about the composition and physical properties of the medium. And now we have here some methods to assessment in SML sensor, to measure, to take control of this. One of them are the spectroscopy, that you can analyze the response across the frequency in a very precise way. You can use Fourier analysis to measure each component of the frequency of the light signal, electro impedance tests, how interaction of the analyte and the metallic surface affects the sensor response. You can use computational analysis, mainly the FENC, that is finite element methods. You can use it to predict the sensor behavior in different scenarios. It can be simulated to in the time you put it in real life, minimize the chance of errors that occurs. And you can use the machine learning to learn all the to train a machine learning to learn all the patterns of the sensor and to collect more precise results and more to minimize the errors. So, in conclusion, here we discuss some comportments in different situations of the that electrodes of the sensor can be used, like shrink them, apply current, and how to analyze with computational methods, some computational methods. And these are just an idea, don't have any concrete conclusion, but it's more like this article that we wrote is more like to discuss if each of these methods move a little more than we said here. It was like a abstract of them. And yes, in this, and I want to acknowledgement to FAPESC, the CNPq, the UTFPR, and the UFPR to help us in the experiment that we made at the start of the year, that we made a 3D impression of support for sensor that we take to Curitiba to make some tests, and we wrote one article for LaWolf's in May, and we made a sensor of fiber optics, and I should be brought here the result, but we made a little surface resonance in our sensor. Paterno brings, I think he yesterday in his presentation he brought the graphic that we made, and I think is this. Thank you for your attention.
Thank you so much, Afonso, for your talk. Now your time for questions. We have some questions. I have one quickly question. If you are thinking today in develop SPR sensor in fiber optics, what will be the configuration you choose based on your review in the literature and the modeling simulation? What is the best design, in your opinion, based on that?
Sorry, what do you mean about design?
The configuration of your sensor for the SPR.
We made a sensor, a support for sensor start of this year. Is a 3D printed way that we put the optical fiber in this sensor, and we took to Curitiba to then enhance the optical fiber, and this enhancement of the optical fiber enables it to take off the cable of them, and we choose and goes to the nucleus of it. And then we made these experiments using the 4 electrode. I don't think we used the 4 electrodes, we used the 2 electrodes way, and we could achieve the surface plasma resonance.
Thank you so much. Some more questions to Afonso? So, just thank you, Afonso, again. Thank you for presentation, very good work. And now you are closing this section for this morning. I'd like to say thank you so much for all the speakers of this morning. We have a very fruitful discussions and was wonderful works presenting this morning today here in the event. And you are going back at 2 p.m. here in this auditorium for talk of Professor Eden Morales. Yes, blessed be the fruit for this section today. And in my case, you'll be having the short course in the laboratory number 14, D14 in chemistry department. So you are very exciting to meet for these also activities, and let's have a good lunch now. Thank you.
in Brazil, and I really admire your country. I really love it. Thank you so much for everything. So my topic today will be dealing with nanophotonics for the next generation of biosensors, and biosensors, especially for healthcare, and some of them related to food quality and other topics. So I think the transitions are not working. Okay, thank you. Perfect. So let me invite you, all of you, to visit us in Mexico. We are in Querétaro, which is more or less at the center of the country. We are in UNAM, Autonomous University of Mexico. Of course, you can visit us whenever you want. We have a fantastic environment. The city is very lively, and we have some appealing places as well. So my team is devoted to the study of nanophotonic phenomena. So we study nanophotonics, interactions between nanomaterials, and we give them an application for healthcare, in vitro diagnostics, environmental monitoring, and also food analysis. We generally employ sustainable materials and also nanomaterials. We have a couple of perspectives, actually more of them, related to sustainability in sensing and biosensing. So maybe you are familiar with these terms. The next generation of biosensors is sought to meet these requirements here. They should be real-time connected. If we have real-time connectivity, we can access, for example, the Internet of Things, the cloud computing, and so on. Easy to sample collection, that's also very important, which is also related to user friendliness. It should be environmentally friendly, as the future technologies, I think. It should be affordable, sensitive, specific, user-friendly, rapid, robust, equipment-free. So generally we have to reduce the equipment we need to read the sensors or biosensors, and they should be deliverable to end users. So we are working to achieve this kind of requirements using nanophotonics. And we think that the next generation of biosensors will facilitate personalized, non-invasive, and preventive healthcare. So, for example, we are striving to generate disruptive analytical platforms. For example, we wouldn't like to depend on tissue analysis to get a diagnostic. Instead of this, we would like to analyze blood or plasma, serum, urine, saliva, and using the next generation of sensors, we can also analyze easily accessible samples such as tears, sweat, interstitial fluid, and also breath. So let me introduce these wonderful materials. We make everything, almost everything, with bacterial cellulose nanopaper. This is a multifunctional biomaterial. This material is fabricated by this bacterial strain, Acetobacter selenium. It's a sustainable material. So you feed this bacteria, and they grow for you this fantastic cellulose nanopaper. It's biocompatible, biodegradable. It is also optically transparent, flexible, lightweight, with high mechanical strength, also high thermal stability. And this is very important for us because we modify the material with nanomaterials, with optically active nanomaterials. So this is an example of conventional paper, but if the fibers of the paper get smaller and smaller, you will have nanofibers, and they are optically transparent because the light interacting with these fibers has wavelengths which are much bigger. So these fibers are about 50 nanometers or 10 nanometers. It's highly hydrophilic, so you can have hydrogels, for example. It's got high porosity, high surface area, and it's basically made of cellulose. So with basic chemistry, you can modify the material chemically. So we can load or we can attach covalently or physically trapping nanomaterials such as metallic nanoparticles, quantum dots, upconversion nanoparticles, in general, optically active nanomaterials. So let me just remind some basic concepts on plasmonics, some nanoplasmonics, because we use nanoplasmonics for sensing and molecular sensing as well. So as many of my colleagues already said, with metallic particles, metallic nanoparticles, we can have a very active cloud of electrons, and this cloud of electrons is able to amplify light hitting the surface of the nanoparticles, and we call this a plasmon, or a localized surface plasmon resonance. And this phenomenon this depends on the size, the shape, the composition, the interparticle distance of the nanoparticles, and also the refractive index or dielectric properties surrounding these metallic nanoparticles. So we can use these parameters for sensing, for example. These are just some examples of the materials that have these plasmonic or nanoplasmonic properties, generally gold, silver, but we also have some non-noble metals which are also plasmonic. For example, aluminum, copper, iron, and so on. And we also have the general spectral range for these materials. So remember this, please remember this collection of silver nanoparticles, because as I previously mentioned, the plasmonics of these metallic particles depend on the size of the particles itself. So if we have very small particles, we have this light yellow color. If we increase the size, we also we change the color of the suspension of these plasmonic materials. Then we go to strong yellow, almost orange, and different colors depending on the size of the nanomaterials. So we call it structural color. And keep in mind this principle, because we are using this principle to generate some UV sensors or sun exposure sensors. As you know, this is a critical parameter for us as humans, because if we get too much sun, we can damage our skin. It could be just a brief damage, but we can also acquire cancer depending on our organism and also our exposure to the sunlight. But if we don't have enough sun exposure, we can also have vitamin D deficiency. So we have to keep a very delicate balance. But the problem is UV radiation depends on several factors, including cloud cover, ozone, altitude, season of the year, Earth's surface characteristics, latitude, land cover, time of the day, and so on. So for us as scientists, the question is, how can we measure UV exposure in an easy way using, for example, nanophotonics? And on top of that, moderate sun exposure is strongly recommended by experts in healthcare. So we came up with this idea based on nanotechnology. We have a patch, a wearable patch, which is made of cellulose, and we embed silver nanoparticles. And we knew that silver nanoparticles can interact with UV light, and when they interact with UV light, we can, let's say, we can release some silver ions, and if we release silver ions, eventually these silver nanoparticles will be smaller, so we can change the color of the device because of this phenomenon. So this is the sensing principle. It's pretty simple, and also the device is pretty simple. Special thanks to all my students who will be appearing generally in this part of the slides. This is a wearable device because we really believe, together with my colleague, Jan Dinger, we really believe that wearable devices can be a game changer in the next generation of sensors and biosensors. We have this book, which is commercially available, so this is just an advertisement. And we also have a Nature Reviews materials related to wearable sensors. So in this paper, we have a very nice overview on wearable sensing technology, and we also have an overview on the building blocks that you need to build wearable sensors, which could be very, you will need a lot of integration, but they can also be very simple as this device that I am showing right now. So this is the starting material. This is the nanocellulose loaded with the optically active silver nanoparticles. Then we dry this material. Once it's synthesized, we dry it. We have an adhesive layer, and that's ready to be worn. You can wear it. So we have several tests. For example, we did several tests with several skin types, and our major concern was this group here, skin type 1, skin type 2, which are prone to acquire skin cancer because of the UV exposure. So this is a moderate dose of UV radiation, 15 minutes under one sun. So I mean 1,000 watts per square meter. This is a moderate UV radiation. So we did several tests, and we confirmed the working principle of the device. We had this change in the UV visible absorbance of the device. So we have a left shift, which means that the nanoparticles are reducing in terms of size. And we also studied the population of the nanoparticles embedded within the nanocellulose, and we confirmed this phenomenon. But we have a second generation because of the color of the device. So we needed a contrast. We needed an agent of contrast, in this case called nanoparticles. They do not change color because of UV light. Only silver nanoparticles change in color because of UV light, as I previously explained. So, well, we don't have the GIF here, but well, you can. If we had the GIF, you could see the color change of the device. So it's a tattoo-like device. We can use it. We can wear it. I mean, So this is the color change of the device from yellowish to reddish and vice versa. We again confirmed all these phenomena using SEM microscopy, UV visible analysis as well. And we are very happy because this work was mentioned in this Nature Technology Future along with other colleagues who are working in light-based sensors. So we are also producing CERS substrates. I mean, some substrates made to amplify Raman spectroscopy. For those who are not familiar with Raman spectroscopy, I will give you I will offer you the fundamentals of Raman spectroscopy. When we have a sample and we excite this sample with a monochromatic laser, we can have scattering of this light. Most of this scattering is scattered at the same wavelength, and we call it elastical scatter or Rayleigh scatter. But a very small fraction of this light will be Raman scattered. It means light bounces off the sample at a different wavelength than that at which it entered because of the interaction with the bonds or with the composition, let's say, of the sample. And this is fantastic for us because the molecules have a very specific fingerprint in Raman spectroscopy. So we can identify molecules in a very specific way using Raman spectroscopy, and it's got applications in cultural heritage, chemistry, catalysis, biology, biomedicine, and also diagnostics, environmental science, and in general in measurement science. But as I mentioned before, a very small fraction of this interaction is Raman scattered. So just 1 out to 10 to the 6th photons enters, let's say, into the Raman field. So it is really desirable to amplify this effect, and we can do it using nanoplasmonics. So if we have a couple of metallic nanoparticles, these nanoparticles, as I previously mentioned, will be able to amplify the light, which is hitting the surface of these nanoparticles, and they will put the light in a very specific region, of course at the nanoscale, and we call these dramatic places of light amplification. We call them hotspots, and we can use these hotspots to amplify Raman spectroscopy. So we are producing this CERS, surface enhanced Raman spectroscopy substrates, also using nanocellulose and graphene related materials, especially graphene oxide, and also metallic nanoparticles. In this case, we have silver nanoparticles, and these substrates are let's say, flexible, and naturally you can also wear it onto your skin. So this is a very important slide for me as well, because we are again using graphene oxide, but this is, let's say, the rationale behind this decision. We are using graphene oxide because graphene oxide quenches the sample fluorescence, which is a problem. It's a general problem in Raman spectroscopy. So it also prevents CERS substrate degradation, especially for silver nanoparticles. It also facilitates the attachment of organic compounds via pi-pi stacking interaction. So we can have another kind of amplification. We have a charge transferring phenomenon that also enhances CERS behavior. Graphene oxide also masks the CERS signature of our main material, which is cellulose. So this is very nice for us as well. And we can also, using graphene oxide, the surface chemistry of graphene oxide also improves the density of metallic nanoparticles. So if we have a high density of metallic nanoparticles, we also have a high density of hot spots, as I previously mentioned. So it also improves the electromagnetic field enhancement factor in CERS, well, at least in nanopaper-based CERS substrates. So we studied, for example, the stability of these CERS substrates, and we saw that after 50 days, we had a very stable Raman signal. We had practically the same limit of detection for this system. Here we are using rhodamine 6G as a model analyte, and after 120 days, we saw a slight degradation of the signal, but again, it was very sensitive. We have nanomolar limit of detection in this case, and then we came up with a new CERS substrate. In this case, we have graphene oxide flakes as well, but in the middle of these flakes, we have gold nanorods. So we have these layers which are self-assembled, and in the middle of these layers, we have this gold nanorods. So we have a very novel material, and we studied the light interaction, or the interaction with light of this material. We also have some COMSOL simulations. For example, here we are simulating the interaction of the substrate with light. As you can see here, we have a formation of what we call web of hot spots, which is huge for us, because you can let's say produce Raman amplification practically everywhere, as long as the analyte is embedded within these hotspots. But they are practically available everywhere, and this is huge. This is huge because actually we also discovered that these hotspots are, let's say, remotely excited. So we can propagate plasmons across the volume of this three-dimensional substrate, and we can create a web of hotspots, and we can detect molecules remotely. I mean, the molecule couldn't be inside the field of view of the apparatus, could be outside, and although it is outside of the field of view, we can also detect the molecules remotely, because the material has this property. So we have a transmission of plasmons. So we have a web of plasmons that is transporting these hotspots and also CERS signals. And this is huge because we can detect very low limits of detection of the molecules, and we challenged, let's say, this CERS substrate in several ways. For example, we dropped just a few molecules. Let's say, yes, in this case, it was about 10 molecules in the center of the substrate, which is 6 millimeter, 6 millimeter, and we performed a scanning using Raman spectroscopy, and we found the Raman signature throughout the complete CERS substrate in a three-dimensional way, not only XY compositions, but also in the Z axis. So it's very sensitive. And we have several proof of concepts with these materials. For example, we can analyze some extractions of corn. Here we have corn, different brands, for example, this is white corn, this is also white corn, and this is blue corn. And probably these two types of corn were contaminated with pesticides, probably, but not this one, which was the blue one. And we also analyzed the surface, just with a very simple smear process. We analyzed the surface of food, for example, some fruit and some vegetables, and this is really alarming for us because we found this ramen peak, and this ramen peak is associated to micro or nanoplastics. Could be strongly related to nylon. So it means that we could be eating, let's say, agrotextiles such as nylon. And we found it using this technology, but of course we need some other techniques to verify this. We are also analyzing sweat using this cell substrate, so we can reveal the presence of different metabolites in sweat, and also as a very novel biofluid to be analyzed, we are analyzing sebum, which is very, very novel. So our view is to produce spectral diagnostics using cells, using cells, our cell substrates, and also artificial intelligence. We have this point of view published in Trends in Analytical Chemistry. So we can analyze easily accessible samples, let's say saliva, urine, sebum, sweat, and we can generate a database with this kind of analysis, and after that, using artificial intelligence, we can have what we call smart diagnostic, but based on Raman spectroscopy. We love paper, so for example, we can also do some paper-based devices. This is a smartphone and paper-based reader for quantum dot signal. This is a pretty simple approach. Everything is made of paper, and we also use this smartphone here. Actually, the filters of these, the optical filters for this approach are also made of paper, and we can measure the photoluminescence which is emitted by quantum dots in this case. And this is also very important because we are also contributing to the real-time connectivity that I mentioned at the beginning of my talk. And we can also have smart diagnostics if we have an interoperability, interconnectivity of our biosensors with other platforms. So we also have some immunoassays based on graphene oxide as a quencher of fluorescence. It is very important to keep in mind, when it comes to graphene materials, it is very important to keep in mind the quality of the material in terms of lateral size, in terms of number of layers, and also in terms of carbon oxide ratio. If we change any of these parameters, we change the properties of the material. So that's very important to keep in mind if we are generating new approaches, new devices. So let me introduce quickly this FRET, fluorescence resonance energy transfer phenomenon. So when we have a donor of photoluminescence, it should have an emission which is overlapping the absorbance of an acceptor. It could be another fluorophore, but it could also be another material. So we have we can have a dark quencher in this case. So for example, graphene oxide is a dark quencher, so we don't have emission, but we can have this quenching of photoluminescence using graphene oxide. Typically, we have this limit for a common FRET, 10 nanometers. It is observable up to 10 nanometers, but using graphene-related materials, given the properties of graphene-related materials, we can have up to 30 nanometers as an observable phenomenon. So this is a pretty simple example. For example, if we have this graphene oxide, or in this case, this is a graphene flake, and we separate the graphene flake different distances, we will see a distance dependence phenomenon which is observable up to 20 nanometers. When they are very close, this FRET, this energy transfer, is very efficient, so you can almost completely quench the emission of these quantum dots, these photoluminescent nanomaterials. And you can do the same using graphene oxide, for example. And importantly, graphene oxide and graphene-related materials are also known to be universal quenchers. So it means you can quench the emission in the red channel, the green channel, the blue channel, because the absorbance of graphene-related materials is very broad. It practically interacts with the whole spectrum, so we call it optically omnivorous. So here the question is, how can we revolutionize the immunoassay field? As some of my colleagues previously presented the famous ELISA test, we have the famous sandwich configuration, and in the middle of each step we have time-consuming washing steps, and we also need a blocking step to avoid unspecific interactions of the analyte with or any other molecule with the substrate. In this case, a polystyrene 96 well plate. So this is the gold standard of immunosensing, but it's time consuming, and here, for example, you at least need two antibodies, a capture antibody and also a detection antibody, and with this detection antibody you will display a colorimetric signal, let's say, depending on the concentration of the analyte. So can we simplify these kind of assays using nanophotonics? And the answer is yes. For example, we have this approach here. So we modify the bottom of the wells, the 96 wells. Note that these ones are black ones because we are working with photoluminescence. We are not working with colorimetry. We are working with photoluminescence. So this is why we need these black ones. So we modified the wells with graphene oxide, and we studied the interaction of immunoreactions inside these wells. So we noted that when these antibodies, let's say, are free, when they do not find the analyte, and if these antibodies are labeled with a fluorophore, they have a very high affinity against graphene oxide. So we will automatically quench this fluorescence, which is coming from the antibodies labeled with a fluorophore. In this case, we call it a probe, which is a fluorimetric probe in this case. But we discovered that when we have these immunocomplexes, I mean, when we have the analyte or the antigen which is binding the antibody, this complex here has no affinity against the microwell coated graphene oxide, so automatically we have a very strong fluorescent signal. And this is also huge for us because we do not have washing steps, we do not have blocking process, and we only need one antibody. And so we are reducing time, we are reducing waste, we are reducing cost as well, using nanophotonics again. So we tested this configuration with different fluorophores, for example, emitting in the green zone, emitting in the red zone, and also with different analytes, for in this case prostate-specific antigen, the classical one, which is human IgG. This is pretty could be a standard immunoassay. And for example, when we performed a proof of concept to detect prostate-specific antigen within urine, I mean, we doped urine with this antigen. The immunoassay was pretty quick. Within 10 minutes, we were able to detect the analyte. But when it comes to conventional ELISA, it could take more than 6 hours. We also have this application. It's the same working principle, but in this case we are detecting E. coli. So we are detecting bacteria, and we did it in a collaboration with a company which is devoted to frozen food. So they provided us with some frozen food, contaminated and free of E. coli in this case, and we were able to confirm their results based on cell culture using our technology. We also have a translational stage of this approach. In this case, we are devoted to women healthcare. It is devoted to bacterial vaginosis diagnosis. So we analyzed more than 160 vaginal swabs using our technology. In this case, the target is sialidase, which is a biomarker for bacterial vaginosis. And this is very important for women who are how to say that for young women, I can say that. So we have a very nice calibration curve, and we perform this let's say translational approach, and we have a very nice sensitivity and specificity, which is about 96%, both of them. And we also have a point-of-care device, again for bacterial vaginosis detection. So we have the same working principle, but this time it's executed on a paper strip. So we have this device, which is very small. It could be 2 centimeters, like from here to here. So one of these arms is modified with graphene oxide, and we use these arms to reveal immunoassays. So if we have a negative result, we will quench the fluorescence of this arm, of this let's say chip zone. But if we have a positive result, the fluorescence will be emitting light in both sides of the let's say of the chip. I mean, the control zone will never be quenched, and the test zone will be quenched or not, depending on the formation of immunoreactions. And again, we tested with real samples this device, and we had a nice behavior again. And we also have some contributions to the pandemic scenario. For example, we have this review article where we highlight the impact of biosensing, the role of biosensing in a pandemic scenario such as COVID-19. And we also generated COVID-19 seroconversion assay based on the same technology, and we also analyzed some real samples, and we succeed to distinguish some pre-COVID-19 patients from COVID-19 positive patients as well. And we have other applications of the same technology. For example, we can calculate protein kinetics using the same platform because we can analyze the binding of the analyte with the antibody in real time. For example, we can see here. So, in doing so, we can determine the affinity constants related to this binding phenomenon. And well, I mean, this is a different application, but it is also easy to execute. I mean, and with the same aim to simplify immunoassays, we also have this approach. This is a zeolite embedding silver clusters. So these silver clusters are known to be very sensitive to their surrounding medium. And if we modify this, the medium of the clusters made of silver, we can also modify their photoluminescence. And we discovered that when we capture the analyte, or when we capture the antigen in this case, the fluorescence of these silver clusters also increases. So automatically we have a biosensing assay using this new technology as well. And we did it again for IgG detection and also for bacteria detection, E. coli detection. Again, we succeeded to do that. And well, this is quite much what we do in the lab. Special thanks to my colleagues, all of them. Of course, we are in a Women in Sensor session, so I would like to mention this. This cover is devoted to women in science. So we have a couple of covers devoted to women in science which were designed by Diana. She's our, let's say, she's the scientific illustrator in our team. We have international collaborations, and of course, I'm looking forward to collaborating with Brazilian colleagues. Yeah. Just a final advertisement. If you are working on biosensors or analytical chemistry sensors, please submit your approaches to analytical chemistry. If you are working on photonics, you are encouraged to submit your work to JFIS Photonics. We also have some special issues in biosensors and bioelectronics, and also in green analytical chemistry and other journals in which I serve as an editorial board member. So thank you. I will be very happy to discuss these topics with you.
Any?
Thank you, Eden, for your good presentation.
And by congratulations for your brilliant career.
Thank you, thank you.
Good articles.
Thank you so much.
And I have a question for you. Raman spectroscopy is destructive or non-destructive?
It's a non-destructive technique.
Ah,
Of course, you could destroy the sample if you use a very high power, but generally you use a very low power and you do not destroy the sample.
it's possible use it
Directly on the skin?
Yes.
Yes, I saw some approaches that are doing Raman spectroscopy on the skin. Yes.
Oh,
Yeah.
okay. And are there small Raman equipments,
It-
or is a big
Yeah,
equipment in laboratory?
A very nice question, which could be done in this this topic. When it comes to this approach, we use conventional Raman spectroscopy, a benchtop Raman equipment. But now we are working with a portable Raman, which is offered by Hamamatsu. It's something like that. Very small. Yeah, very small.
But expensive.
Not very expensive,
Oh.
this one, but not. But I think I asked for a pricing recently, and they told me it is not on the market anymore because of some component. So, but anyway, there are people working on portable Raman spectroscopy. We would like to acquire a high quality portable Raman. It should be, well, it should be bigger.
Okay.
Something like that. And this is not particularly cheap, but it's really, really powerful. Yeah.
Oh, nice. Thank you.
You're very welcome. Thank you.
Can you just turn the volume down? O volume está muito alto.
Congrats, Professor, for your talking.
Thank you.
And,
Thank you so much.
It's a curiosity for me. What do you prefer to work on using quantum dots or using fluorescent if you want to see the...
Yes, this is a very nice question. In terms of budget, I prefer fluorescent because it's very, very, very cheap. In terms of signal intensity, maybe I could prefer quantum dots because quantum dots have the advantage to be excited with different wavelengths. So you can use UV light, you can use green light, even red light, and you can have a very, very high signal, fluorescent signal from the quantum dots. In this case, those which are emitting in the red zone. Yeah.
Did you test using your system that you developed, that you show us that you developed a system like a smartphone to...
Well,
I think so the starter of a presentation.
Yes,
so
I
that
think
you
it's
developed a smart...
Yeah, we tested this. It's
yeah,
over here.
So that's here.
Yeah, should be here.
Because it's very exciting to if using a lateral flow test.
Yeah, that's true. That's true. We didn't have time to do a lateral flow test in this case. Laura was doing a master degree, so we didn't have time to do the lateral flow test. So we simply analyzed the different concentrations of the quantum dots, and that's it for this work. Yes.
Very nice. Thank you so much.
Thank you.
Any further question?
So you mentioned quantum dots are a lot brighter. Have you ever tried using those brilliant violet fluorophores that I think they got on the market a few years ago? are the product of a Nobel Prize in chemistry. Do you know that they're similar to antennas, molecular antennas? They're incredibly bright and stable, much better than quantum dots.
Yeah, well, I haven't worked with molecular antennas, but, only with quantum dots.
I know that when I read about quantum dots on flow cytometry, it sounded amazing. I never got my hand on them, but a few years later, these reagents came out, and they're way brighter and more stable than quantum dots, a lot easier to use. They're revolutionizing flow cytometry nowadays. The flow cytometers were geared towards fluorescein, and now fluorescein is a detail, and these fluorophores are the most useful ones. They changed the whole design of flow cytometers based on these fluorophores.
I didn't know it. Thank you.
Yeah.
It's good to know. It's good to be aware of this.
Yeah.
Thank you. Thank you.
But the question I wanted to ask is, you showed that when you use the graphene oxide quencher, you decrease a lot the processing time for ELISA.
Yes.
But did you test the sensitivity of the assay? I know that fluorescent ELISAs are really sensitive, but did the modifications you make change the sensitivity?
Yeah, this is a pretty nice question. Yeah, for example, to do a one-to-one comparison, let's say, in this approach, we also have a ELISA test, and we improve the limit of detection. I don't have it here, but the limit of detection should be at the sub-nanogram per milliliter level, which is comparable to an ELISA test, but our ELISA test gave a higher limit of detection, so it's a little bit better than that of the conventional ELISA.
But you need a fluorescent reader, which is more expensive, right?
Yes, that's expensive. But for example, if you develop one of this fluorescence reader was $8 or $7. Yeah, you can have it cheaper. Yeah.
Any further question? No?
I have a lot of questions, but so when you had the skin paper, how is that attached to the skin?
Yeah, this is a very nice question. You can use medical adhesive. You can use a medical adhesive, but you can also use tattoo paper. For example, so you can buy it from the market. You can print anything onto this paper, and it's adhesive. Yeah.
It's what?
Like a patch. Yes.
A patch.
Yes.
Patch. I see.
Yes.
And so how could you see like me and my kids using that as a consumer?
The minimal.
How could you see me and my children using this, like for sun exposure?
Yeah, you can simply explain to the kid. Okay, you will be wearing this patch. If you see that it turns red, just let me know, and it's time to go far from sunlight or renew your sun cream. Yeah.
Could you put sun cream over that?
I don't know. No. You cannot put sun cream on that, because it will also protect the detector.
Yes. But then it's that really caught my interest, just because with kids with fair skin, you never know when your protection has gone away and when it becomes dangerous.
Yeah.
So that's my first question, and then Some of the paper that you're working with, is it all biodegradable?
Yes, yes, it's bacterial nanopaper. Actually, people are doing compostable clothing using
Yes.
yeah compostable clothing, compostable shoes using bacterial nanocellulose.
Could it be used as in the seafood industry? There is a huge amount of waste of plastics, with vacuum sealing fish. Is it possible that you could incorporate this with like measuring food shelf life stability?
Yes.
And replacing like a vacuum sealed bag with maybe this kind of maybe it wouldn't have to be vacuum sealed if it adheres. The only reason you use vacuum seal is to get it tight to it.
Well, it's got a lot of pores, so you
Oh.
cannot produce a vacuum with
Okay.
this kind of material.
Would it be protective though?
Maybe
To a
I'm not-
degree.
Yeah,
Okay.
at certain degree. But we also have a device to measure the freshness of food using the same principle. Because when you have, for example, ammonia, when you have fish decomposition, fish spoilage, you have ammonia and other volatile organic compounds. And these compounds also perform an etching on the silver nanoparticles, and you will also have a change in color because of this. Yeah.
They have that out in the market right now, or something similar.
Yes.
Yes.
Yes. Yeah.
Cool. Well, thank you. I really enjoyed that. That's very impressive. Thank you.
Thank you.
Okay, we don't have time for further questions, so I thank you, Dr. Edding, for your brilliant presentation. Thank you.
Thank you.
Now, following up the presentation is Dr. Rosa Amália Firman Dutra from the Federal University of Pernambuco, giving us a lecture about new trends on biosensors for health. Thank you.
Thank you, Professor Pedro. I don't know if he's stay here. So much for inviting me to stay here. It's a great pleasure for me. And my talk is the name is Professor Pedro, no? New trends on biosensors for health. I would like to introduce by myself. I'm professor for the Federal University of Pernambuco. Recently, I was ingressed in the university, the Federal University. I was before in State University of Pernambuco, and not this because I think so. It's 50 years ago, and so now I'm professor of biomedical engineering department, and my research area is biosensors. My background is electronic engineer, but after I got a PhD on biotechnology in areas of biosensors, and you go for until today. My talk is about the health problems in Brazil, and I would like to present my interview on biosensors, especially in immunosensors, that the areas that want to have more challenges and dilemmas to overcome. And so some strategies for immunosensors developed by our groups include nanomaterials and different transducers. So this is for only to reflect about the Brazil. This is a big country, okay? I'm I know that is a big country with big countries. Okay, it's a big, it's big, it's really big. And you see the different situations and health and the disease questions, because Brazil, there are more smartphone than people. It's very interesting reflection. In the list of the human development index, the Brazil has a distribution asymmetric in the distributions. When you see the different situations like this in the north of the Brazil, where the health problems normally is the infectious diseases like the AIDS, tuberculosis that became with AIDS, arbovirus, including dengue, chikungunya, and the Zika virus, and malaria, bacterial diarrhea, hepatitis, and the neglected tropical diseases such as Chaga, leishmaniasis, and schistosomiasis. I work with all these diseases in my life. It is very exciting because the problem is normally don't have a good antibody, good antigens to detect these diseases. So this is a situation by Pan American Health Organization that the principal disease that detected in Brazil, the died is including the cardiovascular disease. But it's not true, because I think so that there are many sub-notifications, and so there are many strategies to solve this problem. But I think so that the problem is diagnosis, and don't have how to improve this. And so one the reasons is don't have diagnosis is because don't have access to the populations to the central human service. And so the idea is to develop point-of-care devices for decentralizations of healthcare service. There are many advantages, because you can solve the practical and the economical, and so this is very exciting area. And this is compatible with now the personalized medicine, that is the one person, the appropriate, you can measure by yourself. After COVID-19, there was a mindset for using the auto testing in mundial, in the global situation, and so the market of point-of-care devices have increased. And so you see that the principal market of point-of-care is in glucometer, the method to glycemic, and the lateral flow testings. And so the glucose biosensor market is around 50% of the market, include the point of care that you put a prick of the blood and you measure the concentrations of glucose. You see, this is a revolution, but now there are many technologies more advanced than this. Then we use the continuous monitoring on the use. For example, is in commercial in Brazil. There is no too high prices, but it's possible to buy, right? And the measures in continuous flux the glycemic. Okay, it's only to reflect about the development of biosensors in worldwide. You see the biosensors put on the tongue, in teeth, on worm, and several ways to measure, and put on the skin, and using patches. after interstitial fluid. I will comment in my talk. And so, how these evolutions of biosensors, immunosensors area, and the genosensor areas is only challenging today, because how do you know, when the antibody antigens to interact, is not possible to have a electroactive species. And so it's only a stereochemical relationship between them. And so it's different of glucose. Glucose, you have an enzyme that the glucose oxidase, and so when the glucose reacts with glucose, you generate the electron species that is remove the current is so easy. And so antigen is very small, the 10 nanometer, you see how you can modify impedance, capacitance, or measurements. And so it's necessary to have some strategy to improve the signal, and so to identify the diseases and for using for therapeutic monitoring, like cancer, when it's necessary you monitoring the different biomarkers like TNF alpha, I don't know say now, I don't know. And so, but this technology not only to point of care devices. Biosensors is in laboratory. This is a normal ELISA method and a clear method that is the same principle, but here you have a Biocore instrument that was developed in California, United States, and this is using surface plasma resonance. This is normally in clinical service. There are many equipments using this in Brazil. This technology began 10 years ago. But why point of care immunosensors? You see in COVID-19, our group developed a system for detecting COVID-19. It is very important to have these immunosensors for diseases, for therapeutics, for some, for detecting infections. For example, it's very exciting areas. There are many possibilities, and so normally it's important that it's low cost, because if you compare it with ELISA methods, electrochemical transducers is the same comparison. And so point of care immunosensors today yet is challenges. The problem is you need to have a simple procedure to measurement using an instrument like a glucosimeter, and so this is a possibility to detect, for example, troponin. Don't have electrochemicals today. Don't have any systems for detect troponin using electrochemical systems in commercial stage. And so low cost and reliability, reproducibility, and so on is a problem for these devices. And so our group developing in the long of years attempt to overcome some problems. And our concern is related to the first biomarkers, and trying to choose the best for detecting different diseases. Don't have no one solution, but there are many possibilities. And how the transducers use it is the other concern. What's the best? I know that if you want to see interactions between antigen and antibody, you cannot see the current produced directly. You need to use a redox probe, for example. And so this is a problem. And after that, you need a proof of concept to show the different situations in testings in real samples. Okay, for starting to, a big problem is immune receptors. As you know, biosensors, the name is bio because you need a biomolecule immobilized on the surface. This biomolecule include antigens, antibody, enzymes, and so on. And so you need a biomolecule. And so what's the best? Monoclonal antibody, polyclonal antibody, or biomimetic antibody? And so don't have a response for it at the moment. And so depends of the situation that you want to see. Our group developed using some strategies. One of these is using nanobiomimic sensors produced by plastic antibodies. How to do this? There's a scheme of this produce of the impurity polymers. This is the protein that you want to detect, the biomarker. You put on the polymer into the cavity. You produce several cavities. These cavities, after you remove the template, these cavities detect your analyte. Okay, analyte. They finish to. If you use nanomaterials, you have more cavities, and so you increase the sensitivity. When I said the problem is the sensitivity of these biosensors, because antigen-antibody interactions, the signal produced is not so expressive. You need to improve. How to improve this? Using nanomaterials. Not only electronic devices very robust, but you need to have a surface, nanostructured surface, and several strategies to improve the attractive response to the antigen. And so this is the plastic antibody. Is the advantage, because if you watch it, it's new, the surface. You can reuse it every time without it lose the activity. But the problem is good selectivity. No. So how to improve this? This is our first work of our groups that develop artificial antibodies for troponin T. This is a biomarker for infections. These developed using carbon nanotubes, and this is a protein, a scheme of the protein attached to the carbon nanotubes. And so after polymerization, this protein using the initial groups, you polymerize it, and after that you remove this using XCD solutions or basic solutions, depending of the situations, or using restrictions enzyme to cut this protein in removing the template. And after that, this is a plastic antibody. This is red plastic antibody. And you test this. This is a scheme of the transmissions micrography on UC. I don't know if you see. It's good, so good. But this is a troponin in cavity of the carbon nanotube, and you remove this, and you have a carbon nanotube like involved by the like a polymer, né? And so this is a response to detect the troponin T. But the problem was the sensitivity is not so good, because for infections you need to detect in concentrations of picograms. It's very small, and so it is a big problem. And the second Other strategies use biomedical sensors based on carbon nanotube, but now using polypyrrole. Polypyrrole is a polymer that is a conductive polymer with good that produce a good response, because if you not reduce like the other polymers that is isolating, no? And so it's a good strategy. I think so. That is the first work that he published in this area using carbon nanotube and graphene. Graphene, as you know, there's a nanomaterial is very biocompatible because have a carboxyl groups, and this is not as too so conductive like the carbon nanotubes. Depend of the reductions, and but is good for the biocompatibility. And so in this case we produced biosensors using a screen printed electrode, and the idea is to make polymerizations in one step and put the polymers, the monomer, and the graphene and the protein, and you make a mix, and mix it. After you remove the protein, you have a surface nano extractor like the plastic antibody nano extractor. And so this is very fantastic, because you can regenerate this surface is cheaper than the antibody commercial productions, because if you have productions of antibodies not so economic, no, that is have several steps to produce, and so on. And so this is a response of the surface of electrode after modifications using graphene, and this is the presence of graphene by introductions of this reduction current, and the peak is in minus 0.6 volts, and represents the graphene on the surface, and this is FTIR, the spectral analysis to see the bands of the carboxyl groups on the surface. This is a presence of the group modifier of the antibodies productions. And so finally, this is the response of the antibodies. This is a MIP, the producing MIP, no, sorry, the NIP, and MIP, there is a more increase in the response, and this is a control, okay? And so it was possible to measure concentrations in order to nanogram, and this is how you see this 0.017 nanograms by ml. And so this is responsible on the serum, and this is shown to the control. There is the selective response. This is very nice because you don't use the antibody to produce biosensors. It's very nice because if you use in warm regions or in hot, you prevent the degenerations of the antibody. This is one way for your fabricator of these devices. But and the second options that I prefer in my cases is to develop proteins to specific sites of the epitopes of the antigens, or produce aptamers. There is our group has collaborations with Professor Ernesto Marques in the Fiocruz, Pernambuco, and in Pittsburgh University, that this is head of the group, and he developed a vaccine for Zika and dengue virus. And so this is the Professor Roberto Lins. He is a specialist in the development of proteins using density functional theory. So I don't know how to do this, but it's very interesting because you can simulate the interactions between proteins and between antigens and antibodies. You can see different relationships if you're using, for example, graphene or other polymers in between these proteins. What's happening if you change the medium, the pH, so it's very, very nice for your simulating. And so is the way that our group to use. These interactions recently, our group produced biosensors using this protein and show that it's possible you distinguish Zika virus and dengue virus. This is because normally our group worked several years detecting NS1 protein, but no extractor, no extractors. This no belong to the virus. The virus is secreted this protein in the middle, and if it is necessary to measure the level of NS1, because it high is indicated that the infection is in active form. There are many viruses circulating in the blood, and so it's very important to detect this protein. But this protein not only common to the Zika or dengue virus, it's the both. There is 6% of the homology between the two viruses. And how to distinguish this? Using a good protein, a good antibody to detect this. In this group developing the protein, and our group used it in biosensors and detect with the selectivity the serum from Zika virus, from dengue virus, yellow fever, and the West Nile. And so I think so that is a future, because there are many opportunities to detect specifically this. This is Professor Maria Isabel Guedes. She is specialist in the development of the proteins in plants. Oh, it's very nice. You inject the DNA on the plants. I don't know if it's possible, but only the plants, and produce the proteins in great amount, and by leaf from the plants. And the idea is using vaccine or antibodies or diagnosis in general. And this is our last work showing that NS1 glycoprotein is common to the two viruses. It's upsetting. I didn't want to publish this, because this is negative of our before working of our groups, but we checked this, the same antigen NS1, and that is present in dengue and Zika virus. This is the result. It's possible to detect Zika and dengue with depending of the expressions. Here is in serum, dengue and Zika. And the system is a film produced using a redox probe for measurements. When you see the decrease of the current in signal represent the amount of the antigens or antibody that, in this case, when the antigen is interacted with the antibody immobilized on the surface, you detect the the protein. The amount of the protein depends on the intensity of the decrease of the current. And so, this problem is that using the redox probe, because the redox probe is a new step before your measurements. And so you have a surface, and after immobilizing antibody, you interact with the voltagen, and so after that you put the redox probe for measurement. And so it's one step more, and there is problem that is the contamination, passivations on the surface. And so the signal produced is contaminated by this redox probe. And mainly if your surface using carbon nanotubes or polypyrrole, and because this redox probe have a iron. Here you have a carbon directs many interactions, and so attaching the probe on this surface. And our concept, this is a result, and our concept is to produce platform that you can use in point of care. Despite, I'm upset again because I resolved a problem, but many problems that I want to resolve, because has a point of care device, okay, but the problem is a new step to put redox probe. There is contaminations of the surface because this redox probe contain iron. So okay, not so good. Iron is species, electrolytic species, and so you need to have a differential, or you need to have a two surfaces to make a differential response. And how to overcome this? The idea is, this is the first one of the first work of a group using polyalamine in carbon nanotubes for dengue virus, using NUS1 detections for this is justified because these proteins, before they appear, the IgM response or IgG response or EGA response, and this is early in the this is normally the peak is in before 4 days when you have a hemorrhagic dengue. And so our work was develop a surface. This is for you have idea that how it's complicated to detect this protein in the past, because normally you use the second antibody labeled with enzyme. Here you use a redox probe for this is contain hydroxy peroxidase for reduce this enzyme for reduce, yes, oxide or reduce, depend of the situation, and you see the response, okay. And so to modify the surface with carbon nanotube, you put polyalamine, and after that you mobilize an antibody, and you make all that several steps. But it's a good response. It's possible. I don't know if you can see this because it's very clear. But you see the control, the system was tested in super network of culture of dengue virus, and here there are responses okay, higher than the control. This is the dengue virus, okay. And so this is very nice, okay. But the problem is the first, this is a conventional electrodes, and so not so good for point of care, you need a redox probe. After this, you need a second antibody and 3 steps to incubation and to see the response. Not so good. What you can improve? After that, use direct response using a screen printed electrode developed of our group. We developed the ink, carbon ink, and after that, you prepare the surface with carbon nanotubes, and after that, you immobilize the antibody against the NS1 protein and blockade the surface because you see the response, decrease of the response after interactions with antigens, and so this is results. The NS1 is better, the concentration is good, the clinical levels in blood, okay, no problem, but the problem is that you needed to redox probe. How improve this? This is our results in comparison to the serum and PBS, and this is how you modify the matrix to measurements, and you see if it's near to the 100, this is okay, and so this the error is 102 minus 100 is 2% of the error. So the error is minimal. The curve is very nice, okay, but the problem is yet using the redox probe. How to solve this? The idea is to measure directors. It's a possibility to use a label-free detections using direct detections without second antibody. This is for troponin T, the cardiac biomarker. This is carbon nanotube is modified with is functionalized with amino groups, and after you immobilize the antibody in the oriented way. Okay, after that, you can measure the direct response. This is the comparison of the surface of electrode with the carbon nanotubes, and it's simple, disposable, and perhaps can be used in the central cells of health. And the idea is to measure the concentrations in level of the infractions, the limit of the text is in picograms. It's very slow. It's possible. This is the profile to comparing the control and the serum here, spiked with the troponin T, and you see the difference of the signal. It's possible you see the cutoff that is good for this real situation, and so these devices can be used on this healthcare service. Okay, and I wanted to improve the system more because the problem yet the use of the redox probe is one problem, and so the challenges that you want to solve is don't use the redox probe. How to resolve this? Our idea was you use the redox probe incorporate on the surface of the electrode. The idea was very difficult. When I sent the paper for the journal, no, rejected, no, don't, okay, but I insist. And so I'm seated now has the revolutionary solutions for immunosensors and the third generations of immunosensors because don't use redox probe and the surface. When I published in Biosensor Bioelectronic Journal, I think so. There's just one for this reason, and so the challenges was right reproducibility, good precision, and low cost, and so step by step, and produce the carbon nickel screen printed electrode. Oh my God! I think the battery. It's okay? Okay. And 2 minutes. Então, então this problem was to solve normally in electrochemical measurements you need to have 3 electrodes. Normally you use a reference electrode, working electrode, and the count electrode. In reference electrode, normally using chloride como é proteína? GCl, Eg. But our idea is to remove this, use all the same ink in all electrodes for producing in large scale, and because normally you need two steps to produce. You put the carbonics, after that you put the AgCl, the how to say it in English, I don't know. I don't remember, but silver ink. And the idea is remove this, and I prove this concept. When I proved, I tested this system for detections of the DNA for microRNA for cardiac. I think so. The idea is to show that is the same that if using silver ink in the third electrode. This is okay, very nice. There are many colleagues that are working with this system now. Professor Cecilia, for example, she used now this system that use 3 electrodes with the same ink. And the idea, finally, is why using redox probe 3. And so the idea is measure directly when you interact antibody with antigens, you don't generate ion species, and you necessarily put a redox probe that can produce damage on the sensor surface, and the signal is reduced or increased depending on the situation. This is the first work of our group, showing the possibility to don't use more redox probe. We used graphene modified with ferrocene, and so this is the background stations of the electrode. This is response of the ferrocene graphene. The peaks in binos is very interesting because don't have contaminations of the metabolites on the blood. Normally, you have the uric acid, ascorbic acid. This is oxidized, and the positive potentials. If you apply the positive potential like a glucometer, that is 0.7 volts, you oxidize these metabolites. This is very no good because you have a response to contaminate with this species. And so, idea of our group is to put the redox probe on the surface of the electrode, and the measurements was possible to measure directly. So, this is the this biosensor story, because I think so that I put it 2 times. And the cystatin C is a renal biomarker for failure, And so the cubes detected when you put the serum, the response is directed immediately using a screen print electrode. Okay, it's very nice. You can modify this for any situation. The limit of detections of this is nanogram. It's very nice, and can be applied for other protein. This odd possibility on this is the Juno when I use the tyramine, the other polymers, but it's polymerized on the sensor surface. This is the the clean electrode after you polymerize the polytyramine, and you put the carbon nanotube in the orientated form, because in vertical aligned carbon nanotubes, the signal improves. This is if you put in randomic positions the carbon nanotube on the surface, you don't have a good signal. Okay, if you put aligned, direct response is increased. It is on the way, and after that, you see the response directed by interactions. So don't use it. It's hot versatility applied to the cobalt phthalocyanine and the carbon nanotube modified for this as a pseudo capacitor. What is a pseudo capacitor? When I see the electrochemical surface, when I saw yesterday when capacitive, the professor from Australia, he told us there is a impedance, but they normally have a capacitance effect produced by charge in the surface. The name is the electrochemical capacitance or quantum capacitance. This is produced by the different ions on movements on the surface, that if you apply a potential, this produces a redox capacitance. If the specific potential, you can measure this current. And so, if you use, for example, I work with conductive polymers like polypyrrole and P dot and the other polymers. You see this modification. And so, sorry, because no have a good. This is a calibration curve of the system using immunosensor for detect B-type inaccurate peptide. This is for cardiac no infections, but if you have a failure on your system, you see the productions of the ischemia. I think so that this peptide is more selective than troponin T. And this is for Zika virus, the work using the redox probe-free immunosensors that produced by the peptide that produced by a group that I mentioned previously. It is a good result. You can see the selective response and Zika and dengue virus. So you can using this principle for any applications. This is one possibility to use for for detect of plastic antibody using for amyloid, beta amyloid is a peak produced by the carbon nanotube decorated with copper, and this is a peak. And the same principle is to produce the protein. A plastic antibody is developed, and you have a redox probe. Don't necessarily use more redox probe on the surface, okay, on the solutions. And so you eliminate it in one step. This is very nice. Other possibility, our group in to pivotal to other, because probably redox probe doesn't work. We have other solutions, and so this possibility just measure the capacitance directly. And so the idea was developed 10 years ago when I used a capacitive device, how to say, and the idea is to measure the difference of the electrical field between the two areas, but two regions, and the difference between the protein mobilized on the dielectric, two possibilities. Our group work with a silicon nanotube and polymers. These evolutions, troponides is important. I don't speak about this, and so the idea is to have the direct response by antibody interactions when the antibody is mobilized on the surface of the device, and after that, when these interactions occur, you can see the modifications of the capacitance. This is the graph showing the capacitance affecting different frequencies. It's possible to have a good resolution if you're using 1 kilohertz. It's very nice because if you can measure this is using a multimeter. It's so very nice, economical, low cost. This is the idea. Our group development in the several advantages. And how to improve this? This sensitivity not so good in milligrams. Not it's possible to measure troponin for infections, only measure protein. What is the first step? And after that, we simulate for using polypyrrole. This is a conductive polymers wrapped with the carbon nanotubes together and put on the surface with nanomaterial and the conductive polymers. And so after that, for example, you see the difference of the electrochemical signal. Here is the barrier electrode. This is modified with the polypyrrole and carbon nanotubes. This is the difference of areas, represent the capacitance. If you integrate these areas, you see the electrochemical capacitance. This is one possible. Our group work developing and ongoing this project for measure to have two capacitance, real and imaginary. Like spectral impedance, you have two capacitance, and if you measure the redox capacitance, you can see in low frequency you can see the interactions antigen-antibody. This is the work in development of our groups. This is a good response. This is work was selected by the journal for the head cover. This is difference when I use the antibody mobilized on the sensor surface, but the difference was that we not used redox probes for measurements like our colleagues. We proved that it's possible to measure the difference of phases, showing that if you produce a pseudo capacitor, you increase the sensitivity, you can see the interactions on the one protein in this order. Okay, so it is a good result. This was hardcover of this region, the journal colloids on the surface B. This is the idea starting, and so there's a long way to stay in this stage now. And this, our group developing for applications to cardiac biomarker and renal failures biomarker. So this is all. Well, recently, I had a pleasure to work with this work with a group of Professor Sanjeev Sharma in the Swans University in Wales, and he showed me the problem with wearable biosensors. Wearable biosensors is very exciting area because you use a measurement direct on the interstitial fluid, use microneedles, are very nice, okay, but there are many problems to resolve. What's the problem? The principal problems that I tried to resolve was that when you put the needles on the skin, normally they flat the needles, and the second problem is the bio fouling, by incrustations of the phenol. Proteins can bind, biofilm can produce it. This is a problem for commercial system that you use 50 days, but the problem is the baseline is changed by time. And I would like to comment that this system cannot apply to immunosensor, because if you need the redox probe to measure the signal, it's impossible. Or if you use aptamer using a label. And so my idea that don't use redox probe perhaps can be used in this system. And the idea was why the different baseline was produced, because the biofouling factors change the measurements, and the patient normally has a low levels detected. You see the problem? If you now buy glucose, okay, but no problem. Problem because the baseline changed along the way, and it's a disaster. And the Professor Sharma invited me to develop an idea, and using a polyaniline film. The problem is I did comment this biocompatibility. You cannot use it yet, prove that is okay. Nanomaterials like carbon nanotubes, graphene, or etc. It's necessary you change your pivotal for other solutions. And so I use the polyaniline that is very used. We use the polymer, not to biodegradable, but combining with the polyacrylic acid, and to produce a hydrogel. Hydrogel is biocompatible, and perfectly before polyacrylic acid, after polyacrylic acid. This is you see the reproducibility of the surface, and the idea is to enclausurate the surface of the electrode, and after that you can see the results. And so after this system was checked in 3 hours, you see in different situations for electrodes, and the variation was minus 50%. So this is a good result. And the idea is to develop more system, more stable, to continue the research. But it's very exciting areas, and you can solve some problems. This is our group developing a dedicated system for this possibility, like this, the system for detect the NS1 protein and the other. Use a dedicated system, and I have a startup. It's my crazy options. And so, in summary, I like to show that the synthesis of nanomaterials is a good idea for your control the properties of the surface, and using good films produced by conductive polymers. These are good. In the develop good protein to detect specific proteins, body or antibody. Okay, thank you. I'd like to thank my team. My team is so big. This is I, and the Congress, that symposium, a local, and they have a collaboration that I would like to thanks each time that I present something, because without them it's possible to come on CNPq, FACEP, and Health Minister, and I belong of the ENCT of Bioanalytics from Professor Lauro Kubota, and so thank you for your kind attention.
So we thank you, Professor Rosa, for your presentation, and we are open for questions.
Thank you, Professor Rosa. Very, very good work. I am excited with troponin monitoring. It's possible use troponin monitor in a wearable device.
So this is a good question, because when I was in Swansea, I would like to work with troponin, but my colleagues told him that no evidence that troponin level is okay in ICF. No,
Okay.
not yet. It's necessary to convince the research group that is.
Okay.
Because the level is very low. I think so. That's femtogram. I don't know.
Okay.
Or perhaps doesn't.
And in subdermal fluid.
Subdermal? No. In sweat? No. I think so. That's no.
Oh, okay.
But saliva is okay.
Okay.
Saliva and tea.
Okay.
I think so. That's
Sure.
possible.
Okay.
Yes.
Okay. Thank you.
Thank you.
I'm excited
Thank
with
you
your work.
for your attention.
Any further question from the audience?
Maybe a very simple question, because I'm not an electrochemist. Why do you need the protective layer onto the electrodes, screen-printed electrodes?
Protective layer, because normally you have a passivations on the surface. Normally have a passivation. No, if you use, for example, a redox probe, that is contain the ferrocyanide and the iron is impregnated to the surface. Okay. And in development, in the measurements, if you have a, for example, for point of care, you need a velocity response. And how can you measure interactions? For 50 minutes, you see the interactions, a good interaction. The cube, okay, we can wait in 50 minutes. And after that, this redox probe impregnate on the surface. You need to have a good system for calibration this. And this is a cost for your production. So if you put on the surface very sensitivity, or if you use pseudo-capacitance measurements, perhaps on the way, it's a very, very good idea. Our group is pivotal to this area now, to see the using conductive polymers, using incorporations with the redox probe, electrocatalytic surface, natural, not necessarily using redox probe, more.
Nice.
One step.
So I remember an approach that had a labeling of the target with glucose, for example, and then you can simply use a glucose reader to detect something. So what's your perspective on this approach?
Yes, because I think so that for enzyme biosensor, no problem. It is also easier to detect, because enzyme that oxide reducing enzyme natural intrinsic properties. The enzyme, like a glucose oxidase, when they see the substrate, have a magnetic field that attracts the surface, and after that you change the ions, and after that you scratch the ions to the surface. And you can measure this in current produced. And in antigen bar, not. DNA is the same. If you have a single strand DNA with the interaction or the hybridization, no signal is producing. It's different of the enzymes. Enzyme for glucose now, I think so that is new perspective, new trends for the wearable biosensors is to resolve these problems of the baseline biofouling, because this is a really problem for long stage. And it's not so cheaper, not so one biosensor about 200 reais in Brazil. One electrode, not the system, the electrode. And you see, you use it for 50 days.
Yeah.
The system is very expensive, but the possibilities is sweat. I think so. That's one possibility using iontophoresis.
Yeah.
Our group trying in these directions to lactate. This is for they developed the system for the lactate. That's for athletes, high level athlete, but it's possible to use it for clinical applications too. But normally it's for this. And glucose is a principal market of biosensors, and have some problems yet, not resolved in all situations. For point of care, okay, no problem more. But for using continuous monitoring, or if you're using in several or saliva, or but it's good because in children, for example, if you have a prick all day, my God, this is very decisive. I think so. This is very cruel to be the shine, and the future is to modify this for the situation. So,
thank you very much, and congratulations on your excellent work. Thank you.
I insisted. Thank you so much for.
Do you have any further question?
My question is, how hard would be to detect lactate from sweat?
How hard? I think so. That's not so too hard. Too hard is more difficult. More difficult to detect. For example, troponin. Troponin, the level is picogram. Lactate, no. The current produced is in order of microamperes. No, it's a good current.
So is it better than detect glucose on sweat?
No, depends of the enzyme. So because
Okay.
depends of the enzyme, the quality of the enzyme.
So you mean the enzyme which is on the surface of the sensor?
But the problem of biofouling, you see in two situations, both in glucose and the lactate detections.
So that means the enzyme combine with the lactate and do kind of a reaction.
Yeah,
And
yeah,
you detect the reaction.
Yes.
Detect by color or by just measuring the conductivity?
Detect by produce of the current.
So you have to measure the current.
The current, yes. You apply the potentials in this potential. The potentials can modify using several strategies, like using mediator, chemical mediator, or using nanomaterials, and so. Normally, for glucose commercial, you're detecting 0.7 volts. 7.
So as you measure a resistance, just put two probes on it and measure the resistance or the capacitance.
No, you can for enzyme you have if you use a because if you use an enzyme you have a different situation. You have reductions or oxidation or reductions of the product, but in antigen bar only stereochemical interaction. Don't
Okay.
produce the signal. Okay, different of if you use enzyme. There are different enzymes, but I speak about the glucose lactate that produce oxidations or reduction of the substrate.
Okay. Thank you very much. Thank you.
Thank you.
We are ready for the coffee. And after the coffee, we have a 3 poster session that will be done in this room. Okay? Thank you very much. Oh, by the way, the bus today to the hotel, you know the time, I sent some message, which is 6:45 because of the poster session. Okay, and tomorrow the bus will be 8:15 a.m. from the hotel to here. Thank you very much. And another news, another is that I'm still waiting some of the invited speaker to send me the boarding pass. If you don't send them out the boarding pass, you have to pay the ticket. I'm not kidding. Thank you.
Does it need to be? Do you need the paper or a picture?
If the picture is not good, I need the paper.
Because I took a picture of all 11 of them.
Yeah, it's better if you use the scan app. There's a scan app in your mobile. Scan it better than a picture. Okay.
Oh, scan is better than a picture.
Oh yes, absolutely.
Okay.
Thank you.
Okay. So we can start just for our closing section. So in the name of the organizing committee of this conference, and most specifically about the Women in Sensors, the WiSE, this was the first edition of the WiSE Day in Biosensor during the event, and I think it was very good opportunity to know different works doing by women, female researchers in this field of biosensors, not only in the academic environment, that most of the time were more close as academic student and so on, but we have also very good experience in her talks about people who are doing biosensors work in industry and also in start a company that you can talk about the work of Dr. Gabriela. I think this was very also inspiring for the new researchers, young researchers, students, see the possibility you translate the technology that you are performing in our laboratories for society. So I think this is one of the goals of this event. So other very positive points is you have the interaction with the students and the networking that was established in this event that I think is most important. It's a small event, but this also make people closer and with the opportunity to talk and discuss science, discuss technology, new ideas. So I think this was very important point that I would like to highlight in the today. And the other very important thing that was also discussed by Professor Pedro that did wonderful work in organizing this conference, Professor Pedro, and all your team. Congratulations for that, because you got a very good view about this event, inviting people from different fields in biosensors community. And for example, I never had the opportunity to talk with a scientist work with bioimpedance, and I learned a lot about this during these last days. So I think this is very important to have a meeting that are combining chemistry, engineering, biologists. You have Professor Fernando, I have opportunity to interact with him, people that are working design of antibodies, proteins, peptides, so different stages and different fields regarding the biosensing technology. So I just would like to say thank you so much for people also that was home attending, watching these talks, for all the colleagues that presenting today. Unfortunately I missed the wonderful talks of Professor Eden Morales and Professor Rosa Dutra because we had the short course at the same time. But I think this is very important was the connections you are building during this event, and this was a kind of a construction for next year. You do something even more big and involve even more people with more different fields regarding the biosensing community. So thank you so much, everybody. Oh, yes, the next WiSE Day. Alaska.
The next WiSE Day, WiSE Day 2024,
5.
Let's think about.
Yeah, let's think about. I will not commit to myself right now. But let's think about who can do something nice together and try to push for funding. And Professor for organizing a very nice meeting also that I think is important. We still having this conference for sure, for sure.
This workshop was programmed to be 2 years.
2 plus 2 years. Okay. Mm-hmm.
My plan is to do another workshop on applied biosciences in 2026.
6.
So even, no even, or odd, no even, in even years. 2, 4, 5, 2, 4, 6, 80, 0 as well as even. So 2026. But as far as I know, WiSE Day happens every year.
Every
Is that
year.
right?
Yes, we
So-
did the one in December in Mackenzie.
Yeah.
Just today's event. And now here in Joinville, in
Why not
Desky.
in Pernambuco?
I think it's very most attractive place
Oh,
actually.
you are here, sorry. Why not in Pernambuco? Yeah.
Very
why not?
attractive place.
Very attractive place, Recife. Yeah. Thank you. Bye bye.
Thank you so much.
So the bus, I'm trying to set up a bus 6:15
Okay.
today
Mhm.
from here to the hotel.
Mhm.
Okay.
Perfect.
And tomorrow will be 8:15 from the hotel to here morning. Thank you.
Thank you.